2026, and we will begin with the first session entitled Quantitative Precipitation, Estimation and Hydrological Applications. The session will be chaired by Professor G.S. Bhatt, IISc Bangalore, and Dr. Sachin Pandey, Scientist, Indian Institute of Tropical Meteorology, Pune. May I now request Professor G.S. Bhatt and Dr. Deshpande to take their seats on the dais. I now request Dr. Chandan Kalita and Vibhashri to felicitate Professor G.S. Bhatt with a Fulam Gamusa. Okay, sir. We now move on to the first lead talk of the session, an overview and recent progress of the global satellite mapping of precipitation GSMAP, to be delivered by Professor Ushio. I now request Professor Ushio to take his seat on the dais. I request Dr. Chandan Kalita and Vibhashri to felicitate Professor Ushio with a Fulam Gamusa and a memento. Professor Tomo Ishio, senior member IEEE, is a professor whose work spans radar-based remote sensing, atmospheric electricity, and spaceborne observation of the atmosphere. He received his BS, MS, and PhD degrees in electrical engineering from Osaka University in 1993, 1995, and 1998, respectively. After completing his doctorate, he served as a postdoctoral researcher at the Global Hydrology and Climate Center in Huntsville, USA. He later joined Osaka Prefecture University as an assistant professor, followed by appointments at Osaka University, where he became professor in 2019. From 2017 to 2019, he also served as professor at Tokyo Metropolitan University. His research encompasses thunderstorm characteristics, instrumentation, electronic discharge, atmospheric electricity, electromagnetic compatibility, phased array radar, radar remote sensing, and satellite-based microwave remote sensing. Professor Ushio has also held key research positions, including visiting researcher at the National Research Institute of Earth Science and Disaster Prevention, and currently invited researcher at NIED. He has received numerous notable honors, such as the Prize of Outstanding Technical Paper, Institute of Electrical Engineering in Japan, Presidential Award for Achievement, Osaka University, the Commendation for Science and Technology by the Minister of Education, Culture, Sports, Science and Technology, NASA's Top Discoveries in Microgravity Recognition, the Osaka Science Prize, Prize of Progress, Institute of Electrical Engineer in Japan, and the Horiuchi Award from the Meteorological Society of Japan in 2020. He also plays an active role in scientific leadership, serving as Associate Editor of IEEE Trans Radar Systems, Editor for the Journal of Atmospheric and Oceanic Technology, and committee member and co-chair for several national and international bodies, including the American Meteorological Society, IUGG, IAMS, ICAE, and Japan's Ministry of Internal Affairs and Communications. His extensive academic research and advisory contributions continue to advance the fields of atmospheric remote sensing and radar meteorology. We welcome you, sir. The session is over to you. Thank you.
Thank you very much for your introducing me. So today I'd like to talk about the global satellite mapping of precipitation, which we call GS map. That is a global precipitation map with 10 kilometers and 1 hour resolution. And well, okay, thank you very much. Right. So before talking about the detail of the GS map, so I'd like to ask you, so have you ever heard or seen the GS map? Okay, thank you. Right. So maybe more than half of the audience do not know well about the GS map. So please allow me to talk from the beginning of the GS map. So GS map is a hourly global rainfall data with the resolution of 10 kilometers and 1 hour. So this product has been used by more than 12,000 registered users from more than 150 countries or regions all over the world. And the unique advantages of the GS map is listed here. So first, space-based rainfall observation allows to capture the rainfall even in the area lack of ground-based observation. Rainfall can be measured globally, continuous at the same interval, and consistent accuracy. And the GS map data is very open, freely available by FTP site in JAXA. And also, this has a very GS map has a long-term archive data for more than 25 years, since 1998. And before coming here, so I looked at the website of the GS map, and this is a distribution of rainfall over India for about 72 hours from January 1st this year. So you can see, so almost over India, it was clear sky from the beginning of this year. And I think that is consistent with the feeling or your days at the beginning of this year. And this app has so many various application fields like climate monitoring, weather monitoring, water-related disasters application, agriculture application, energy application, and public health. So, for example, if we look at the drought and heavy rainfall monitoring, so this is one example of the drought index in Australia in December 2019. So if you look at, right. Okay. On the left, you will see some colors of drought index. So if you look at the over Australia, you will see the red colors. That means the less rainfall event compared to the annual average of Australia. So, and also if you look at on the right, this is a heavy rainfall precipitation percentage compared to the annual rainfall average. So this kind of indexes has been used, for example, in Australia or other countries all over the world. So what kind of sensors does the GS map use? So currently there are 3 kinds of sensors, as you know. Those are precipitation radar, infrared imager, microwave radiometers. And for precipitation radar on satellite, so on the first and second day of this iRAD conference, you saw so many presentations about that. So, but however, in the GS map, we mainly use infrared imagers and microwave radiometers. So implicitly, GSMAP uses a precipitation radar as a database in terms of climate, right? So, so as you know, so infrared imagers basically that measures the cloud top temperature, and they cannot observe the precipitation directly, as you know. So, but on the other hand, in the case of microwave radiometers, that basically measures the intensity of microwave radiation that is constantly emitted from raindrop itself. So they can estimate the spatial distribution of precipitation with wider swaths, and actually there are so many microwave radiometers in operation. So the main sensors should be microwave radiometers in the GSMAP system. And so, for example, this is one example of the observation result by precipitation radar, infrared radiometer, and microwave radiometer at different two frequencies, that is 90 gigahertz and 85 gigahertz. So if you look at the panel A, that is measured by the precipitation radar system on TRIM satellite. So you will see a very detailed structure of precipitation in band type echoes. So this is regarded as truth, right? So, and on the other hand, if you look at the observation result from the infrared radiometer, so you will see the very, very large area with low temperature side. So that is not necessarily correspond to the actual precipitation patterns, right? As you know. So of course, infrared radiometer gives us some information on cloud top, but however, it is not related to, it is not necessarily related to the surface precipitation rate. But however, if you look at the data from microwave radiometer at 19 gigahertz, which is the panel C, so you will see some correspondences with the result from precipitation radar. But however, so if you look at the over Kyushu Island in Japan, so you will see very, very strong emissions from land itself. So over the ocean, we can use the data from 90 gigahertz channel, but however, over land, we cannot use it. So if you look at the microwave radiometer data at 85 gigahertz, you know, the area is a little bit, you know, wider compared to the emission from at 19 gigahertz. So, but however, it is not. It is, well, you know, it is. But however, it is closer to the actual rainfall pattern compared to the infrared radiometer data. So it is very, very important to combine the data from different frequencies to retrieve precipitation. Wow. Okay. So in the case of lower frequency, for example, 90 gigahertz or 10 gigahertz or 80 gigahertz even. So that frequency detects emission signal from raindrop itself. So if you have many raindrops, that means it means large emissivity. So this method cannot be used over land due to its large emission from the land itself. So as I said, so but however, if you move to the higher frequencies, that is 85 gigahertz or higher, so that detects scattering signal from snow or ice particles. So if you have many ice particles, that means large scattering effect. That means so observed microwave decreased. Okay, so more ice in the upper level often means that the rain clouds have developed to a high altitude. So we assume this correlation and estimate heavy surface precipitation if sensor detect large scattering signal. So that is the basic idea to retrieve the precipitation rate from microwave radiometer data. So, but however, all the microwave radiometer are on low Earth orbit. So if you want the global precipitation map with 1 hour resolution, so this is a coverage of all the radiometer data from all over the world. So you will see some large areas which was not covered, which has not been covered by all the microwave microwave radio metadata. So that limits the temporal resolution of the global precipitation map. So some area cannot be covered with merged microwave rainfall data in 1 hour. Okay, so we need to fill the gaps between the microwave overpasses. In order to do that, so GSM map uses the data from the IR images on geostationary orbit. Okay, so there are two kinds of. How can we realize this? So there are two kinds of approaches to combine the data from the infrared radio metadata and microwave radio metadata. That is, one is the IR-based approach, and another one is the moving vector approach. So IR infrared-based approach uses mainly direct conversion of the brightness temperature at infrared wavelengths to precipitation rate. That is the basic concept. So generally, the lower temperature, the higher rain rate, right? That is true. But however, it is also well known that IR-based rainfall emission estimation sometimes has large error. So compared to that, in the case of moving vector approach, they propagate the rain pixels with the atmospheric motion vector, and so that is the basic concept of this type of approach. The main advantage of this type of approach is they have the relatively high score compared to the IR-based approach. So, but however, so possible main source of error is that the advection vector is the only process that describes the temporal variation of the precipitation process. That is the main disadvantage of this type of approach. So what is the approach in GSMAP algorithm? So we decided to take the hybrid approach. So that is sampling from both worlds. Okay. So that is, we propagate the rain pixel on the moving vector derived from the successive IR images, and then optimally estimates the rain rate from the brightness temperature at the IR wavelengths. That's the combination of both methods. So what is the best way to realize this? So global precipitation map is, of course, is a sequential process. So Kalman filter is one of the best way to do this, to realize this. So GSMAP takes a Kalman filter approach, that is to refine precipitation rate on Kalman gain after propagating the rainy pixels. And the Kalman gain is determined from the database on the relationship between the infrared brightness temperature and the surface rain rate. So that is the concept of the GSMAP. Okay, so from the successive IR images, we calculate the global distribution of cloud motion vector, and then based on this global atmospheric motion vector fields, we propagate the rainy pixels detected by the microwave radiometer 1 hour before. And then after that, we refine the precipitation rate based on the Kalman filter. So in such a way, so we can have the global distribution of rainfall rate from the infrared, not only the infrared radiometer data, but also the microwave radiometer data. So this animation is one of the examples of the GSMAP product. So you will see some microwave radiometer data from low Earth orbit like this, but between the swaths of the microwave radiometer data, you will see some rainfall distribution after the propagation, based on the propagation approach. Okay, so for example, if we look at the over Japan, so you will see some rainy burns associated with rainy season, and also if you look at the other regions over the globe, you will see the distribution of heavy precipitation rate associated with typhoon or hurricanes. So this kind of information is very, very important, as I said, in many application areas, including hydrology or dam management or river management, and also including the public health. Okay, so anyway, so this is very important. So again, so this is the basic structure of the GSMAP algorithm. So as I said, so geo-IR images, we derive the atmospheric motion vector, and we propagate the ray pixels estimated on GSMAP 1 hour before, and then we apply Kalman filter. Then we have the product called GSMAP NRT now, which is a near real-time product of GSMAP. And then after that, so we also apply the Kalman filter for smoothing. So after 3 days or 4 days later, after the observation, we have the GSMAP, the product of GSMAP MVK. And in addition to this satellite-based product, we also have the gauge-adjusted product called GSMAP gauge or GSMAP gauge NRT. So that is actually the main topic of my talk today. So this is a list of GSMAP product. So the top line shows the satellite-only product, GSMAP MVK, which is a standard product, but that has latencies of 3 days. And so, but some users want the real-time or near real-time product, particularly for water resource management or river management or dam management or something like that. So in such a case, they use GSMAP NRT, which has the only 4-hour latencies, but some users want more. So in such a case, they use GSMAP now, which is a real-time product. But however, the disadvantage of this product is the lower accuracy, right? So, and also, in addition to this product, in addition to the satellite-only product, we have the gauge-adjusted product, GSMAP gauge. So GSMAP gauge also the 3 days latencies, GSMAP gauge NRT, that is the 4 hours latencies. Also, we have GSMAP gauge now, which is a real-time product, but however, low accuracies. So, okay, in addition to this, we are now currently working on some local GSMAP product, which is GSMAP gauge _ country. So in India, so you already have done this kind of research, okay? Which the product is called GSMAP gauge ISRO, as I remember correctly, right? So what kind of algorithm is used in this GSMAP gauge product? This is the basic formula used in this product. So we have, this formula. Actually, the top formula corresponds to observation model, and the second one is a state transition model in Kalman filter theory. And also, we have additional observation model listed here. So before going into the detail, please allow me to explain the first the X, A, and R. So X in this formula is hourly precipitation already estimated by GSMAP MVK, right? Which is a satellite-only product. And in this formula, A, T, is the corrected value of GSMAP, okay? Which is the final product, right? Gauge-adjusted product is A, right? And the large arrow is a daily, that means 24 hours accumulation provided by the Climate Prediction Center in NOAA in the US. So they provide this kind of product with 3 days latencies, right? So in this system model, X, is proportional, linearly proportional to the A, right? Corrected value of the GSMAP, and the time, the precipitation rate at time t is equal to the precipitation rate 1 hour before, but it is not true. So this kind of error is expressed here as W. And also, 24 hours accumulation of gauge-adjusted precipitation should be equal to the actual measurement of rain gauges supplied by Climate Prediction Center, right? So this is a basic model used in the GSMAP gauge. And this is a cost function used in the GSMAP gauge algorithm. So basically, calculation of gauge adjusted precipitation is a map estimation. That means this is a kind of optimization problem here, right? And maximization of a posterior probability means the minimization of its negative log likelihood, as you know, right? So in the optimization problem, this is the cost function, actual cost function, right? Here, problem 1, right? So gauge adjusted precipitation minus GSMAP MVK should be minimized, right? And also, this is time fidelity. So the precipitation rate 1 hour before should not change dramatically at present time. So that's the second term. And also, 24 hours accumulation of gauge adjusted precipitation should be equal to the actual rain gauge measurement. That is third term, right? So that is the basic concept of the GSMAP gauge algorithm. And the solution means here the cost function is a differential convex function, that is the convex quadratic function, that takes a minimum value where the gradient of the cost function is a 0 vector, right? So this is the actual calculation of the GSMAP gauge algorithm. So the most important factor here is that this solution is immediately obtained as a closed form. So that means we can solve this equation only a few minutes with the normal personal computers, very, very fast, and we don't have any ambiguity here, right? So this is very important. This is very, very, very important. In such a way, so this is the distribution of global rain gauge, which NOAA is using. So if you look at over the US, they have so many rain gauges used in this here, and also Japan and Europe. In India, so they have, good gauge measurement in this product. And this is one example of the GSMAP gauge. So the left is the distribution of precipitation patterns supplied by the global gauge measurement. And this is the middle is from only the satellite measurement. And the right is adjusted rainfall distribution in GSMAP gauge. So if you look at over the US, so the satellite measurement has a peak here. But however, actual rain gauge measurement does not have this kind of bright signal here. So if you look at the GSMAP gauge algorithm, it is in the middle, right? So maybe adjustment algorithm is working well over that area. And also, if you look at the over Africa, which is not a dense observation network area, the CPC global rain gauge data, probably underestimate. But the GSMAP MBK, which is a satellite product, has a clear peak here. Okay, so but if you look at the GSMAP gauge algorithm, you will see some, also peak here. Okay, bright peak. So because this is not a dense observation area, right? Anyway, so in this way, it seems my GSMAP gauge algorithm is working well as expected. Okay. So, well, this is one example of the precise comparison over Japan. For example, if you look at the radar rain gauge measurement, which is regarded as the truth in this case, So if you look at the GSMAP MBK, which is a satellite product, you will see some underestimation, but if you look at the GSMAP gauge, which is a little bit improved, okay? So anyway, in this way, so this is a comparison of the radar measurement compared to the satellite measurement in various product. So GSMAP gauge is in red here, correlation is highest, and the GSMAP AVK is a little bit lower. So, and the GSMAP now, which is the real-time product, is worse. And actually, no hydrolysis estimator is lower than that. Anyway, well, so in this way, you know, as is expected, GSMAP gauge has the highest score. The most accurate product is the GSMAP gauge compared to the satellite-only product, which is the GSMAP AVK. Okay. So, and also recently we are now working with Argentina scientists about this. So the left is the observation result of the local rain gauges of Argentina, and the number of rain gauges of Argentina is concentrated on to the densely populated area like Buenos Aires or Cordoba. So using this data set, this is a GSMAP gauge measurement of Argentina, right? So the original GSMAP is here, and the left one is a measurement of local rain gauges of Argentina, and this is a GSMAP gauge AR. GSMAP AR, GSMAP Argentina, like GSMAP ISRO, okay? So the Argentina did the same thing as you know. And the right is the original GSMAP gauge. So in such a way, so they are now working, or they are now using their own product, okay, GSMAP Argentina. And in addition to this, of course, Argentina has another set of rain gauges, which is operated in real time, all right, okay? So, of course, they have 24 hours accumulation of rainfall data measured by local rain gauge network. But however, at the same time, they have their own hourly rainfall data measured by the local rain gauge network. So, how can we use this kind of data? So in order to make our GSMAP gauge in true real time, so we have developed another concept of algorithm, real-time GSMAP. This is the cost function of that product, okay? So the first term is data fidelity, and second term is data fidelity with ground rain gauge, of course, or radar data, okay, here. And also, we have the regularization term in spatial directions and also regularization term in time direction, okay? So with this new algorithm concept, so this is one example of the new real-time GSMAP gauge, okay? So the left is the gauge Argentina, the original GSMAP is here, and the GSMAP gauge AL, which I said, here, and the right is a proposed method. So it's not so bad as long as I see. And this is a real-time operation, quasi-real-time operation. So original GSMAP is on the left, in the middle. So this is a GSMAP gauge AR. But however, if you look at precisely, you will see some artificial patterns of precipitation. Well, if you look at here, precipitation pattern does not change with time. So this is not natural. So on the other hand, if you look at the proposed method here, you will see some more natural rainfall changes. So in this way, so now we are currently working on making it real time. So if you are interested in this, please let's have some collaborations. So I'm very, very happy to collaborate with you, Indian scientists. So in order to do that, I'd like to propose three-step approach. Okay, first stage, second stage, and third stage. The first stage is basically offline processing. So if you give us the 24 hours accumulation of local rain gauge network, that can be included in the GSMP, in the current GSMP gauge algorithm. So I think we have already done this with ISRO people. So then we have this, we succeeded in producing the GSMP ISRO product. And the second stage will be the near real-time 3 days latencies. So if you supply or give us the 24 hours accumulation of rainfall data set in near real time, then we can include that data set instead of the CPC global rain gauge measurement, okay? And now, after that, at the third stage, that is a true real time. So we are now, as I said, we are currently working with the real time GSMP gauge real time. So if you have real time gauge measurement and can send them to Japan, so we can include them in the algorithm. So the algorithm will work in real time and make real-time corrections over that country. I think that will be very, very fruitful to the society in that country. Okay, I believe that. Anyway, so this is a summary of my talk today, and maybe time is up. Thank you very much.
So time for a couple of quick questions.
Thank you, Professor Usio. Now I request Dr. Susmita to escort Professor Usio.
Excuse me.
And
if there are any questions?
questions, okay.
Any audience, any questions?
So please.
GS map journey, and is there any plan to go for much higher resolution from 0.1 to like 4 kilometer?
Yes, we are now working for that also. So,
Okay.
you know, recent Himawari satellite has only 2 kilometers and 10 minutes resolution. So, you know, the first version of the algorithm has already been completed. And we are now evaluating the accuracy of the product. And if the high resolution infrared images are available all over the world, then probably we can move to the high resolution GSMAP stage. So that will be, I do hope that will be realized in the near future.
Okay, thank you.
I want to thank, because there are a lot of, secret admirers of GSMAP product in here. So I'm so happy that they all get to see some of the people who are the original GSMAP source. So especially for the young people in the audience, you should consider this opportunity very lucky, because many of you use that and you just see a name. So, and also, he took a lot of effort to come here. I want to thank him for this.
Thank you.
Okay, now I request Dr. Susmita to escort Professor Usio and settle down among us. The next lead talk will be delivered by Dr. Subrata Das on investigation of extreme rainfall events over Mumbai using a polarimetric X-band radar network. I request Dr. Das to please come on the dais. Please settle in. I request Dr. Susmita to felicitate Dr. Das with a full arm. Dr. Subrata Kumar Das is a scientist at Indian Institute of Tropical Meteorology, Pune. His research focused on mesoscale meteorology, Doppler weather radar, and LiDAR remote sensing. He did his BSc from Guru Ghazi's University, Bilaspur, and followed his up with an MSc in physics from the same university. He did pursue his PhD in physics from National Central University, Taiwan, and he was a visiting lecturer at Guru Ghazi's University from 2002 to 2004, and was a doctoral fellow at the National Central University, Taiwan, from 2005 to 2011. He joined the Indian Institute of Tropical Meteorology in 2011 as a scientist and has been working there since. He has researched LiDAR remote sensing of clouds and aerosols, radar and satellite meteorology, tropopause dynamics, atmospheric wave and design and development of scanning LiDAR. For his excellent performance, he earned a gold medal at Guru Ghazi's University and earned a Taiwan scholarship from the government of Taiwan. He also receives the Outstanding Academic Performance Award at the National Central University, Taiwan for his research achievements. Due to his contribution to meteorological research, he was awarded the URSI Young Scientist Award by the International Union of Radio Science in 2011. Now I request Dr. Das to present his talk. Over to you, sir.
Namaskar and good morning to all. First of all, I would like to thank Guwahati University conference organizer for organizing this conference in Guwahati, and it's a very good place and we have a very nice time. And thank you for giving the opportunity to present this work, which is like we have studied the extreme rainfall event by using the newly established urban radar network of small X-band radars. And the several people has helped us to set up this network because it is quite challenging, as Professor Chandra was telling, that setting up in Mumbai or Oklahoma, Kasa, everywhere there is a challenge of the getting a place. So these are the team like Jagdish, Sunil, Chiranjeevi, Aditya, and Dr. Sachin Deshpande. They have worked in this work, but there are the several other people who has helped us in setting this network. Okay, so the what is the special? Because already Mumbai has one radar. What is the special? Why we again put the small radar network in the same place? Because we need to understand the scale. For better understanding of the processes. So from the urban radar perspective, so this figure we have chosen like x-axis is the spatial scale, y-axis is the temporal scale, which shows that different colors. What those color represents, like blue color relates to the atmosphere, yellow for the surface process, green underground process, red highlights the typical urban process, and purple indicates the problems which we pose to the society in the urban area. So most of these processes in the urban regions are related with this rainfall, and it varies from the temporal scale of the seconds to the meter and hundreds seconds to the hours and the meters to the hundreds of the meters. So the two scales are very important. One is the process scale and the observation scale, and they must both align if you want to have a better understanding of those processes, and especially keeping in mind the hydrological behavior in the urban environment, because nowadays urban flooding is the major problem. Yesterday, someone was telling in Guwahati, the flood due to Brahmaputra river is less, but the urban flooding is quite high nowadays. So the theme is that like this radar network can give us the measurement from the small scale to the mesoscale, which can be better used for the hydrological models to have, because it can give the rainfall information very fast because we don't scan at a higher elevations. So this is the typical 4 radars we put, as Professor Chandra was telling, he has suggested that put like this kind of the quadrilateral pattern. So this is an ideal, and some calculation, because based on this coverage and other pattern, so we followed that kind of the things. And these 4 radars at the engineering colleges and the water treatment plant like Amity University, Panvel, which is the purple color, red color is the your municipal corporation water treatment plant, blue color is your at Juhu, Ville Parle College, and yellow color is at the Vidyavardhani Engineering College. So those are the 4 colleges, and in Mumbai we have put of the glimpse that high-rise buildings, and these 4 radars are separated by a distance of 35 kilometers. And these 2 radars are very crucial because you have to compromise with the observational range 18 dBz at 60 kilometers. You have to compromise with the observational range 18 dBz at 60 kilometers. What is the critical about the 18 dBz? 18 dBz just indicates the rainfalls. Okay, so this is the typical radar measurements. Like this one is your reflectivity, first figure, base product, and this is the polarimetric product, the differential reflectivity, differential phase, specific differential phase, we call it as a KDP. This is the correlation coefficients, and this is the radial velocity. This is from the one radar. I just want to show that this is the radar we are taking a measurement there, and this is the existing IMD S-band radar. This is like 4.5 meter elevation, and this is also IITM, one of the X-band radar at 4.5 degree elevation. You can understand why these measurements are important, because it can do the very rapid scan. And here in IMD you can see there are the some areas where the pixel kind of the things is looking, because this is a very high, that is due to the 250 meter, and this one you can see like a paint kind of the structure, because this is a very high resolution measurement of like 15 meter. So I am not comparing 1-to-1 about those things, but the features are same, and I have not done any the frequency scaling and the corrections. If you do both the part, the figure will look much better. But just to want to show that why these measurements are important. So because it can give that every 15 meter, because the rainfall variability, as Professor Chandra also mentioned, like is one of the difficult part, because it's a temporal and the spatial variability is quite high. And this especially you can see it can give those information at every 15 meters. So these measurements are quite crucial. Okay, so now because this radar is not a typical, its principle is same, working is same, but you cannot use like a typical existing radar, because it are the small radar, and you have to combine those 4 measurements, and they should talk as a single one unit. So for that, these 4 radar measurements are taken from the individual sites. They are sent it to the central server, which we kept in the IITM. And then we create a mosaic. Mosaic is nothing like this radar and this radar, if it is forming, and we can, this radar and this radar forming, we take it, combine it, and form a mosaic. And this mosaic data and the real time, it is available here, because this data set is publicly available, and also we are sharing with the disaster management, state disaster management, and all the MOS institutes, and some research organizations also, like IIT Chennai is also taking for this hydrological model development over the Mumbai. So this is the like just want to show like this is the process. I am not going to tell. The idea is that we are doing the weighing and forming this mosaic. Mosaic means this individual radar. These circles are representing the individual radar, and we are combining, and then 4 radars are combined, and we form it like a mosaic, means like a complete one picture. So you can see this is as good as the existing operational radar, and it can cover the some part of the ocean and Mumbai and on the leeward side. So Mumbai, this side is the leeward side, ocean. So those things. But the most important part is the attenuation correction, because you know X-band radars attenuates. It has advantage of having the small antenna, but it's attenuates. So this attenuation correction is the must before you use, and this is that equation. So we have used so to do this corrections. So now the important is that in Mumbai, the getting a signal is very difficult, because everywhere you will find a clutter from the building. So if you create a mosaic also, because mosaic is just a software and mathematical tool to combine those things, they will always shows you a rain, because you don't know how to eliminate the clutters and how to eliminate those noise. So typically I am not going into those numbers or details, just you can understand a radar signal is a comprising of those spectrum, and it is made of the clutter signal, weather signal, and the noise signal. So we try to plot this power density map, how it's look. So this is the signal you are receiving, okay, the spectrum you are receiving, but you don't know which one is the weather signal. But we know like clutter, another thing, the velocity is not moved, because flutter is a fixed rigid target. So it will be always like a Gaussian shape. So there are the, normally this radar present observation at the lower elevation, you have a lot of the clutter, but in Mumbai, even in the higher elevation, you will have a clutter, because due to this high-rise building. This project we started like in 19, but due to this COVID, everything got stopped, and then the several buildings pop up. So we face lot of this clutter problem. So elevations like 3-degree elevations and above, even though we have put in high-rise building and towers and other thing, but clutters are still there, we have to admit. So then this noise signal is there. Okay, so this black color represents this noise signal, and then you can know that, okay, these are the above the noise, and you fit some kind of the Gaussian curve, and then you can find out this is the real signal, and others are the noise. So this is the quite important, and even though it looks very simple, but you need to do this kind of the exercise when you are going to do this quantity precipitation estimation. So why I am showing this one? So if you say this is the like unfiltered reflectivity, so you will get this kind of the image, and you don't know which are the clutters, the first one, and what are the real signals. So you have to go through that exercise, create some kind of the clutter map, and then you can find out this final intensity. So now, as we are mentioning, attenuation is one of the things we should not neglect, especially in the X band and C band. So this is your measure reflectivity from, this is from the single radar, because you cannot combine and do mosaic and then create what you called this correction. So for this is your measure reflectivity, and this is the corrected reflectivity by using the Z5 algorithm. These are the well established. But to do this Z5 algorithm, you need some coefficients, and those coefficients you can derive by using the T-matrix scattering simulations, and these scattering simulations also need some another input, which is like the disdrometer measurement. So I have not shown all those things, because those are very, very specific and technical. Just you see that measure reflectivity and the corrected reflectivity, there are some change in the color. I don't know whether you are visible. So like yellow become more red and other kind of the thing. So we just plot a ray plot. Ray plot indicate just you take one azimuth and see how the things change. So you can see with the range, the PIA is the path integrated attenuation, and it's like 8 dB. So if your reflectivity is the 30 dBz, by doing those correction at 60 kilometer, you can get like 38 dBz. So that is the meaning in the single simplest form. Okay, what does the attenuation correction do? So that has a lot of implications in for the rain rate estimations. If someone has done that sensitivity, you can see how those values are changing. So as I mentioned, like this is a polarimetric measurement, so you cannot just simply rely on the reflectivity. You need to use the other measurement, what we call as a ZDR and differential reflectivity and the KDP. And you need to know the blended algorithm. Blended algorithm means it has to use reflectivity, it has to use the ZDR, it has to use the KDP. So this is the CSU blended algorithm, but the only unknown variables are those numbers and how those are related. This can only be done based on the scattering simulations. Again, I am saying this scattering simulations part is quite important, and if you don't use properly or correctly, your radar estimation rainfall will not come correct. And then whatever you do some adjustment and other things, these are the best possible things to minimize the error due to the QP. There are the physical sense, there are the several errors, but these are some technical errors you can reduce, and this you can see the ZDR and ZH, how they are related at the lower height, at the lower reflectivity, they are concentrated at the lower ZDR values and then increases. So those things are useful, and this is the Bringi's and Chandrasekhar's algorithm to find out this threshold. So with this you can fill up those numbers and you can derive the rain from the radar. So this is just a typical example I am showing. This is the your rain rate by using the blended algorithm. So you can see the rain rate is varying from like 1 mm to up to 50 mm. And then you can, I have plotted this one, that what does the blended algorithm do? In the same PPI, you have to use R, ZDR, KDP, which is the green, R, KDP, which is the red, and ZR relationship. Even the ZR relationship, you should not use the Marshall-Palmer. I will show less. And ZR relationship is the gray color, and the purple color is the R, Z, ZDR. So this is the usefulness of the blended algorithm, and in this way, you have to do for the single radar, and then you can combine it. Fortunately, we have this Mumbai, we have a place like more than 100 rain gauges, which we are maintaining very regularly with a very high resolutions, and this data set, again, I am saying publicly available through mobile app and other things, and this can be also used. So we have done this, the gauge and the radar rainfall comparison. So you can see this blue color is the ARG, and yellow color is the blended algorithm, and green color is the Marshall-Palmer relationship, which traditionally people use. So you can see its blended algorithm really outperform. So ZR relationships, and it is matching quite well for this. The rain gauges, I have shown the few, but in few like rain gauge areas, there are some underestimations. So that may be possible because you know the temporal resolutions, like 4 minutes we are doing the sampling, so we need to do more. But apart from that, you can see this, it is matching quite well with the rain gauges, more or less. Now, this is quite important. You know, this is a comparison between the rain gauge measurement and the satellite rain estimate. So why I am showing, just focusing on this, as Professor Ushio was showing, we have also used the GS map MVK product and the real time CMORPH and iMerge early, late, and the final product. So if you compare those things at the daily scale, it looks excellent. And GS map outperform, it's performing the very good. It's on the daily scale, the correlation. So if you just focus on the correlation, its relationship is like getting close to the 0.8, 0.9. But if you consider this hourly scale, the correlation is the dropping to like 0.3 and 0.4, even this MVK product. So this is showing that in the hourly scale, getting this rainfall information is quite important, and also it is quite challenging. So there was a requirement, even like radar meteorologist people generally don't prefer, but still to combine the radar, gauge, and the satellite to create some kind of the product. So this is some kind of the radar. First one is the radar, and if you correct it with the gauge, and the second with the iMerge and correct with the gauge, and then the rain gauge, and this is the merged product. So this is a spatial plot I am showing, but I will directly go to some kind of the statistics. Here you can understand what I want to say. So this is like first one is like correlation coefficient. So blue color is just like from the radar, correlation is, this is from the hourly scale. Daily scale it is matching quite high. So hourly scale, if you can see, the correlation is like 0.6, 0.5, it is oscillating radar and satellite, but if you consider and combine with the gauge, it is coming close to the 0.10. So this Taylor diagram is the good indication. We have used the two-way Kalman filter and the cost function to do all those exercises. Those technical terms we can discuss offline also. But this Taylor diagram is quite useful. So you can see gauge and radars, they get like 0.6, 0.5 correlation with the rain gauges. Again, I am telling on this hourly scale, not in the daily scale. And if you consider create some merge product, it is going up to like 0.9. So we also done some kind of the nowcasting. So we have considered the pi steps, and this is left hand side is showing your observation, and there are the three different methods: Lucas, Carneret, DARTS, and VET. So I am not going the technical detail. Lucas is just an optical flow method. DART use the discrete Fourier transformation, and VET will use the cost function minimization. So what we have seen this fractional skill score, that this can give a very good reasonable nowcasting up to the 2 hours up to like 0.8 skills. So this is a fractional score, and obviously if you consider 25 kilometer spot, the skill is very, very high. But if you consider the 1 kilometer grid box and want to give a nowcasting, this radar is capable of giving this up to 2 hours. Why we have done all those things? Because these are all the requirement from the disaster management to, because we have these measurements and to show. So now as per the title, we will show like one of the heavy rainfall case in this year, like Mumbai, we got like 300 mm of the rainfall, and this is passing. And what we want to study? We want to study this, what is the dynamical and the microphysical parameters we can derive from here, and how we can understand this heavy rainfall event, and what are the microphysical parameters. So we have also done some kind of the analysis. So this the advantage of having the network of the radar, you can individually combine the radial velocity of the 4, and you can derive this three-dimensional wind u, v, and w, and can study the wind pattern. This is one kind of alternative, even though you don't have the wind profile, which can also give in the clear air. But here, if you don't have, but at least some dynamics you can get by combining these 4 radars and do some study. So this is the vertical wind, like what we have derived, and we have done this convective and stratiform separations. This algorithm we have used like Powell algorithm, which is a refined version of the Steiner algorithm. So this is the convective and the stratiform, and we have constructed the CFAD. So you can see the CFAD, and these scales are different from the convective and stratiform. Convective is going up to the 5 meter per second, and stratiform is confined within the 0.5 meter per second. And you can see this broad structure. You can see, and then it is like having the maximum positive vertical velocity, which is indicating this your buoyant atmosphere. And if you consider this the stratiform rain, it is a typical signature of the sine curve. And yeah, this measurement was done and shown by Uter and House, and you can see the structures are matching because their radars are quite big. They can go up to the higher elevation because they scan up to the higher height. We don't scan that higher, that's why it's 8 kilometer, but you can see the quite nice structure, and the values are within this range. So it has some capability, and this kind of the structure we need to elaborate more to understand the more on the dynamical part of the any kind of the storms. So now with this we try to again further understand what is the core and how it we can understand during the pre-mature and the dissipation stage. So this pre-mature and dissipation stage we have defined by using this IR brightness temperature also radar, and by using the rainfall distribution. I am not going to the detail. So this is the x-axis is the cumulative area containing the vertical velocity less than a threshold vertical velocity as a given height. So you can see that premature time the vertical velocity is confined toward the lower height, and this red color represents the updraft, blue color represents the downdraft, and during the mature stage you can see the more of the updraft kind of the pattern, and again during this dissipation type again it is going to squeeze toward the very less updraft and it is dissipating. So those dynamical parameter can also be used, so you can understand why this rainfall heavy rainfall pattern. And now this what is the microphysics means, because you have polarimetric measurement, so you should know the microphysics also. So this microphysics means like this is a CFAD curve, and you can see like from the DBZ, this is a differential reflectivity and this is the KDP. You can typically see this is the classical plot from the Kunjman, and where they have shown this if reflectivity increases, ZDR increases, KDP increases, and it is a typical coalescence process, and which is a thing it is representing for the warm rain process. And we have derived the drop size distribution also from this by using the polarization measurement, and this is a vertical profile of the drop size distribution. You can see nicely the drop size is increasing and the concentration is decreasing. So this is a radar measurement is totally a engineering measurement. They radar don't understand like collisions other thing. It understand the backscattering power we receive. Okay, and then to apply you understand and understand the physics, we convert into the some parameter. So those are the things convert from the radar signal to those processes, and then you connect it with the meteorology. The meteorology also saying like in the warm run process the collisions are happening. So yeah, with that I would like to conclude that this radar means provide not only the three-dimensional structure but also and microphysics, but also about the dynamical parameter which is very useful in understanding. So in the future, so what is our way forward? So in the future, definitely we are planning to integrate it with the numerical and the hydrological model, and to support the real-time urban planning for this flood forecasting. And also this rainfall map is very important. So now with this coming of the AIML, we want to integrate it the more and have the better resolution. And one thing, again, we have to go for some kind of more data quality, because the X-band radar is always having some challenges. So like in solid state radar, you need to do some kind of the fine tuning in the software, because it change. Okay, with the instruments, time and lifetime. So that also we are doing. With that, I would like to thanks, and I can take up the questions. Thank you.
Excellent presentation, Dr. Subrata, and it is the need of the hour for several of the metropolitan areas. So I have two questions. One is basically this 19th August 2025. Could you give some sort of prediction regarding this one, or your prediction came afterwards?
So yeah, so prediction means we are not working on this decision support or predictions, but the thing is that there is a demand that it has to be operationalized, but that is the job of like IMD. Okay. So we are giving those data and images. I think Mr. Amit Kumar is also here. So we had a discussion. The images, data, and everything are going, and they have their decision support system. I think they are integrating, and that is happening.
And the second question is, I was fascinated by the premature and post dissipation stages of thunderstorm vertical velocity plot you have shown.
Yeah.
even during the dissipation stage, a significant portion is dominated by positive updraft. So,
Yeah.
could you?
Okay, yeah. So the thing is that it's this curve is little bit of try to understand. This percent is not like the 100%.
Okay.
It is like is vertical velocity less than the given threshold value. So this is the some kind of the definition means here if you can consider like I can come like this is the maximum part it is dominating like 60%, but here it is the less, so it's less than the threshold, maybe like the 5%.
Yeah.
Is
Okay.
dominating, but
But,
if you look at the simple CFA
yeah, yeah,
kind of the thing that looks like still it has a very
Okay.
updraft. No,
So my question is, whether this type of an updraft could lead to a secondary circulation and reorganization of clusters, especially with regard to MCS and all. We may need this sort of information where self-clustering can happen. So any such
yeah,
insight
so
into
that is kind of the one kind of the feedback process. There is always a question that moisture is doing this MCS or due to this MCS the moisture is coming. That is like a chicken and egg problem kind of the thing. That is always a things because I do this observation, I can tell that this is a preconditioning happening from the maps paper. That precondition is important and do those kind of the thing. And similarly, there are several questions like how the gravity waves can also influence all those things. Then another question comes, what is the role of the cooled pole in this kind of the things? These are all sort of the things we have to look. Thank you.
Manoj,
Thank you.
I want to add, what he has shown is correct, because even at the dissipation stage, it is dominated by some of the stratiform component, and it has a mid-level circulation. Okay, that's why he's getting the updrafts at the mid-level. That could be from the stratiform component.
Yeah, Rashmi was there, I think.
I want to first of all congratulate the IITM team for implementing this long-standing dream of mine, which is network of radars in a metropolitan region. He's not told you this. Looking at the data is only 10% of the activity. Getting the thing running and getting it installed is enormous amount of work. And I have dealt with it myself, and sometimes you don't even have the energy to analyze data after the stuff is done. I'm surprised that you don't have any gray hair, or maybe you are hiding. But that said, what I want to say is you should avoid this initial euphoria, and then there will be a time that the one radar will fail, and then something will go wrong. 99% it's due to power supply, and the electricity will go down. There's nothing you can do. But you have to keep reviving, because there will be too much complacency to say, oh, 3 radars are there out of 4, let it run, and so on. And the second important thing is you will deal with the clock tower problem. If you have a clock tower that shows only 1 clock, that's the time. You ask time, you check. But suddenly you have a clock tower with a clock on all 4 sides. Any layman walking on the street will point out to you that 2 clocks are not showing the same time. So you will have to deal with all these things of this radar is not, anybody can say that. But I think if you survive the initial phase of that, then it's all a smooth ride. So with that, I want to just encourage you, not give up. You guys are at the right age with the right attitude to fight back and all that stuff. Don't give up. Stay there. Because watching this, I think other cities will probably put in more network. This is like a huge milestone, and it's to be celebrated at the Radar Meteorology Conference. Thank you, guys.
Thank you.
Yeah, I will also congratulate the team for setting up the radar. The question I would, rather than a question, it's a suggestion to, are you planning to create any user network, since you have started and you have collected a number of years of data? So it is always good to have a user group that you develop initially so that it will reach to a wider audience. Then I have a question now the Mumbai will have different type of rain. So any analysis being done on the warm rain microphysics process explicitly on that?
Okay. So I just want to tell, this is the website. You just log in and you can get those data. For the academic institute and research institute, we are sharing with the several IITs, and since you are from NSS, so there is no issue at all, and you can take those data sets. Now the thing is that sharing the 4 radars data, someone has to combine it. So again I am telling, this is not a traditional radar, so radar has to be combined and create and have a one, like as Professor Chandra was saying, different clock tower, and then you will say that, okay, here it is, even you will not remove the clutter, because AI, ML, the person who are doing, they never remove the clutter, they use the data as it is and they train, and the clutters gives always a rain there. So this is one kind of the challenges. And second question was the like rain microphysics. So that's why, even though this is not a microphysics session, so I just put this one. So this kind of the microphysics you can derive. This is a microphysics only. Okay, so like raindrop distribution, collisions process. So these are the 4 things I have shown, but if you consider the different season, it will come. This last year only we established, and we have only 1 complete season in 2025 only. So yeah, you can take those data set. Data set is not a problem nowadays.
Okay, thank you very much.
Thank you.
Okay, thank you very much for nice talk. And actually, we in Japan we have similar expand radar networks. So I learned a lot of stuff from your presentation. And anyway, so my question is actually relating to this chart. Have you compared with that characteristics with updraft characteristics? Yeah.
Updraft characteristics with whom?
Yeah, in this case, you are concluding that.
Yeah, this is the updraft only.
Okay.
So positive color is the updraft, and red color is the updraft, and the blue color is your downdraft kind of.
Yeah.
Things.
So my question is, so you concluded that collision and coalescence process is very active in that case, but is that how the updraft structure contribute
I
that
understood.
kind of
So
stuff?
we have to go some kind of the time series kind of the things,
Right.
and we can do those analysis. Yeah, that one I have not done in here, but the data set is there. That can be done, like how the updrafts and downdrafts and how this microphysics is changing. Those things are doable. That's not an issue.
Okay, thank you very much.
Thank you.
Yeah, I think also very happy to see this network being operational, and data is coming and being analyzed. And I hope, as Chandra said, it is sustained. And as several questions pointed out, many things to do work on this. I hope you will be able to do that, IITM team. Congratulations once again. And with this, we thank the speaker and break.
Thank you, sir.
Thank you, Dr. Das. Now there will be a tea break of around 10 to 15 minutes. Tea is waiting for us outside of this hall. By the time, I request all participants to load their PPTs in the official laptop if someone is still left. I repeat, if someone is left, please load their PPTs in the official laptop. And all the presentations will be in this hall only. There is no other sessions going on in the academic building. All presentations will be in this hall itself. Thank you.
Your presentations are loaded in the PC here so that we can save some time. Okay.
Good morning, all. I am Deepa from IMD Chennai. So now today I'll be giving a talk on recurving cyclones through IMD best track data and DWR observations. Tropical cyclones, as we know, are a synoptic scale intense warm core systems characterized by deep convection and well-defined cyclonic circulation. Out of all the cyclones that happen around the world, around 4 to 5% normally happens in the North Indian Ocean, out of which North Indian Ocean, as we know, has two basins, Bay of Bengal Basin and the Arabian Sea Basin. The major portion normally happens in the Bay of Bengal Basin. So in the present study, this is a very primary stage of the study, and for this only two cyclones are considered. One is Gaja cyclone, which is a very severe cyclonic storm that happened in 10th to 19th November of 2018, and the other one, the Michong cyclone in 2023 was taken. That was a severe cyclonic storm. Gaja made a landfall near Tamil Nadu, Vedaranyam, and Michong had a landfall close to North Tamil Nadu and South Andhra Pradesh coast, Bapatla. So this is the best track of the two cyclones. So the two cyclones which taken, Gaja, we can see it is having a southward curvature during its course of action, and Michong is having a slightly northward curvature. And Gaja is having a circular loop formation was also happened, and that happened in the sea. So our DWR Chennai observation is taken for this. And the days where best track and DWR observation coincide, that time is taken for the study. So for Gajat, we have taken, yes, Python is a software used for analysis, and mean track error, RMSE, and maximum error and minimum errors were taken considering the tracks generated using best track and radar derived track. So for error statistics, if we consider, Gaja is having a more, the track generated using IMD best track and radar observation. For Gaja cyclone, the deviation is minimum compared to Michong cyclone. The minimum error is around 5 kilometers and maximum is around 40 kilometers for Gaja. And the maximum error happened post landfall when the cyclone is on the land. Whereas for Michong cyclone, error is around 55 kilometers. Error is in the deviation between the two tracks. And so Gaja shows a better agreement with radar, between radar and best track derived tracks. Gaja is showing a better agreement. This is the track comparison. This is for Gaja. Here we can see when the cyclone is around the ocean, both the tracks are almost coinciding. And here is the maximum error that happened. This is post landfall. It could be due to the land interaction when post landfall. That might be a reason for the deviation. Whereas in Michong, error it's like almost error is happening throughout the deviation is happening throughout the course of the cyclone. This is the track separation also. Here in Michong, we can see that we have sharp peaks, whereas in Gaja, the spikes are limited and short-lived. So this is the conclusion. Gaja, maybe the land friction post-landfall could be a reason for track deviation, whereas in Michong, it was Gaja was a very well-organized system, I must say, and with very structured and well organized, and I was very well defined. So that also could be a reason why the deviation is minimum compared to Michong, which is a very less well organized system compared to Gaja. Thank you.
Yeah, we can take a couple of questions now.
Can you please go back that error statistics slide? Yeah, I think they removed it.
This one, sir?
Yeah, yes. No, there are numbers you have shown somewhere. Some statistics numbers you have shown.
Yes, yes.
Yeah, good. What is the accuracy of determination of the center using DWR data? With like is kilometer, meter, centimeter?
We have used using PPIV method. We have used it for calculating PPIV and
right. But there is some uncertainty, no, plus or minus. You have any idea what that uncertainty is?
Right now, I don't know, sir.
Because there is uncertainty, so therefore I'm looking at why you have second decimal.
Okay.
That is in 10 meters. That's too, high. I don't think it's better than kilometer anywhere.
Okay.
Yeah, please keep that in mind. Thank you.
Thank you, sir.
Okay. If there are no questions, thank you, Deepa.
Thank you, sir.
Okay. Next presentation is from Kameshwari Chala. She will be talking on extreme rainfall over central Indian homogeneous region with associated synoptic features during El Nino and La Nina years.
Good morning, everyone. I am Kameshwari, a meteorologist from India Meteorological Department, and that's why my study is also with the synoptic features associated with the El Nino and La Nina years. Sir, here actually introduction I have been hearing to most of the talks which are only related with radar and radar technology and with latest radar development and data sets. But as I am concerned with a meteorologist, I would be more into the synoptic features and which synoptic feature has an advantage or disadvantage during the extreme rain events or a rain that has been below normal. And that's why I've just given an introduction. But as I go for the objective here, why I chose the Indian summer monsoon, especially between 91 and 2023, where we have the ENSO figures. But in that year also, let me just specify here, during the ENSO time, it is the El Nino and La Nina have their own characteristics and features, so which I have just explained in the latest slides. But to just an introduction to the students and the everybody else, that monsoon is dominating with multiple semi-permanent monsoon systems, which are heat lows and all, which many of them would be knowing it. And also just as a background, I have just mentioned the systems. Second, there is the other synoptic features which are associated with the southwest monsoon. And the final is the remote influencing systems. The remote influencing systems are the El Nino, La Nina and the neutral phases of the ENSO, along with the Indian Ocean Dipole and the MJOs. So these are some global phenomena which do affect the Indian summer monsoon, where we get the excess or scanty rainfalls. In this, to study this, I have just taken the central homogeneous region. The Indian subterranean is divided into 4 homogeneous regions, where the central India is the maximum place where we get the, the rainfall plays a very major role. And as India is an agricultural driven country, and this place, this entire homogeneous region, we have to have a proper yield. So therefore the rainfall that we receive in this area is very important. So therefore, here I have come up with the statistics of the rainfall, wherein the red color, which says the El Nino years, and where we have the scanty rainfall or drought years. The blue, the dark blue with yellow font, is the La Nina years. And La Nina has a specific, this one that we will either get normal or above normal rainfall. But that is the characteristics of the, especially in these 2 El Nino and La Nina events, which are global events. So in this, when we have computed the actual indexes, the JJ, that is June, July, August, September, the rainfall departures from 1991 to 23, especially for the ENSO years, we found that the yellow ones, it is the ENSO, that is the El Nino years, and the blue are the La Nina years. In this, my major study is for the year 2000, where the departure is -19. So being a La Nina year, which characteristically gives more rainfall or above normal rainfall should be the predominantly a major feature, has given below normal, and that also minus 19, and therefore the All India departure also is minus 6. And the ENSO, and whereas the Indian dipole, where we are just 0.08, which is within the normal range. So there is certain kind of a combination. Being a La Nina year, we have not received enough rainfall in that homogeneous region, which is the central Indian part. So for that, this is the oceanic La Nina index, which we have taken from the global chart from the WMO site. And these are the central India departures, where again I have shown it's a statistical map, in the graphical presentation. And I would like to mention here the type of years that was there for the El Nino and the OID, whereas what type of depressions and circulation that had occurred from 91 during the El Nino years, and the La Nina years where we have a 98, 99 and 2000. 98 and 99 shows a strong La Nina with a neutral IOD, but the departure is -3 and -4, which is in the normal limitation. Whereas for the year 2000, the La Nina was moderate, but the IOD was a neutral year. We had multiple 10 systems depressions had developed, but still the departure was -19. So -19, it was very below normal, and therefore in this oceanic context this is the major, the criteria which we use, by that the ONI index is from plus 0.5 to minus 0.5, where the warmer and a cooler averaging of the sea surface temperature, and the dipole mode index is plus and or minus 0.2, beyond which it has a very significant role over the Indian summer monsoon. So here the El Nino years were 2002, 2009, 2015, where we had seen a very sharp reduction in depressions, and there was a dominance of the weak and shallow circulations. And during the non-drought years of the El Nino year, during the El Nino was dominating, was 97, 2004 and 23, with a positive IOD, because because of positive IOD, there was an enhanced activity in the Bay of Bengal. And the transition case was 1991. But for the La Nina years, like La Nina years were 1998, 99, 2007, 2010, where we had a normal range of rainfall. 2011 and 2019 was above normal rainfall for the homogeneous region, and 2000 was a below normal. So when we are trying to understand why the below normal, there was a 1 minute left out. So there was a below normal rainfall, and the region was because there was a lot of circulation. But still the circulation did not give us enough rainfall. So my conclusion here is that we have taken a IOD ka map also, why this particular the monthly distribution, and this has been supported by the IMD's progressive rainfall for monthly rainfall, which we have the maps in our Mausam journal for the 4 individual months. So here there were 10 systems. All 10 systems were developing during the Southwest Bay of Bengal, Northwest Bay of Bengal, but they have not given enough rainfall, though the circulation was there. So mid-level circulation was there, but they have not given enough rainfall, and in one time it was a land depression. So therefore the kind of moisture content which was supposed to be there was not there. So I conclude here that so many systems were there, so because of weak teleconnections, and this year the MJOs were also very suppressed. So therefore, though it was a La Nina year, still because of weak teleconnections and because of these certain localized behaviors and the systems which developed within the sea area did not give the rainfall to the actual homogeneous region which was supposed to get the rain. So therefore, it's not only a La Nina which will decide upon, so we have to depend upon more other factors, maybe because of this radar and other technologies which have been coming up. So maybe those products, now if we see, we can give a better forecast. Thank you.
कुछ है क्या questions? Sir.
Yeah, nice analysis. You looked at La Nina, El Nino, and IOD influences. And when it comes to your long range forecasting, no? Another important parameter used is mid-latitude ice cover, or that mid-latitude influence,
Yes,
essentially.
sir.
Did you look at that aspect in that year 2000?
Mid-latitude aspects I did not see, but I only checked with the MJOs because they have more influence on the sea circulation part, and that particular 2000 year, it was a suppressed feature. And one more thing, what I have also taken from the international journals is that after 2000, the MJOs ka, the interaction and sea surface interaction ka, the entire pattern, there was a shift in that, and therefore the studies after 2000 have been more dominating with the MJOs. So, and this particular year, that this entire MJO was also suppressed. So therefore the equatorial, maybe I have also read one paper of IITM, which also says that there was a weak teleconnections for that particular year, where there was a equatorial heating, which has happened, which is a localized effect, and maybe that was one of the components which did not allow many systems to develop, and those systems were not so strong to dissipate over or give the rainfall over the Indian land area. Okay. They dissipated over the sea area. Yeah. So therefore systems have formed, but they did not give the rainfall to the land area. So no therefore propagation. We have a deficient...
No propagation, basically.
No propagation, yeah, yeah. So that is one of the major reasons. But if maybe further study, I will try to get into that.
Thank you.
Thank you so much, sir.
Okay, thank you, madam. So next presentation will be from M. Danish. Is he around? No. Okay, then we'll move to the last presentation in this session. Alok Sharma.
Hello. Very good afternoon to all. I am Alok Sharma, and I am a postdoctoral research associate at IIT Indore, and today I'll be presenting a talk on the two-dimensional mesoscale convective cell surveillance and measurements during the Indian summer monsoon. So a brief introduction is like the tracking of mesoscale convective cells plays a very critical role, and because it helps in the understanding the dynamics of convective cells, like initiation, growth, maturation, and dissipation. Also, we can understand the effects of size, the intensity, duration, and frequency, like how fast the convective cells are forming and how fast they are dissipating. And the third part is like one of the application is in the validation of numerical weather prediction models. So these tracking can help us to validate the forecast which we got from the numerical weather prediction model, and then the rainfall estimates from weather radar can also be improved with the help of the tracked radar reflectivity data from the mesoscale convective cells. So the data we will be using is from the C-band polarimetric Doppler weather radar based at the Thumba Equatorial Rocket Launch Station, that is the TERLS. And the period of study involves 2 days of the Indian summer monsoon, that is 14th August and 15th August. And the reflectivity observations, basically the pre-processing for this data involves clutter correction. I'll discuss this in the next slide. And we use the TOBAC algorithm, that is topic tracking and object-based analysis of clouds to track the reflectivity of the convective cells. This is the data pre-processing for our tracking. So here we can see that the northeast of the Tulse radar has large western Ghats that induces clutter in the radar observations. So we used a clutter correction algorithm proposed by Tyagi and Das for removing the clutter. And then the methodology. So the first step in the tracking methodology involves averaging radar reflectivity along maximum radar reflectivity in the horizontal 2D direction. So here is the first step of averaging like the composite reflectivity that we made. So with this composite reflectivity, we will have our radar reflectivity tracking. So second step in our algorithm, and the first step in the TOBAC algorithm involves feature detection. So in this case, we can give a range of values in the TOBAC algorithm, like 30 dBz, 40 dBz, 50 dBz, and then it will track for higher reflectivity value above this. So in this case, we gave 30 dBz values, and it will track. Wherever there are convective cells above 30 dBz, it will average at a point, and then it will make the features. So these red colored are the features, and the light gray colored are the reflectivity. Then we have the feature segmentation. So the feature segmentation works on the principle of water shedding. So water shedding, in the water shedding algorithm, we have a peak reflectivity value, and like water flows from top to down, the algorithm, it checks for the maximum reflectivity, and we have the threshold reflectivity in this case also. So the threshold, it goes down, and it checks for the boundaries. So boundaries in this case will be 30 dBz values. Another thing of this feature is, another feature of this algorithm is that feature tracking and segmentation are completely different. Then we have the cell tracking. So cell tracking works on the principle of the next closest distance. So we got cell number 20, 22. So these are all the convective cells which have been tracked for the 2 days. So first we find the features, then we segment them, and then we link them using the cell linking, and then lastly the merging and splitting is performed. And then we have the life cycle of the cells. So here we find in the 2 days, we have the maximum number of convective cells. The count is 100, and the life cycle is around 1 hour. And the minimum number of cells are like very less, fewer than 20. And the life cycle for them is slightly more than 2.5 hours. And this is the cell velocity. Cell velocity is like any feature, if it is going beyond a particular velocity like 25, 30, like that, and then we count them. So here we get that the maximum cell velocity we have is around 24.5 value, and the minimum is like the higher velocity values are always on the lower side. So this is the area of the cell track. So as we see, from the initiation up to dissipation, so it has a lifetime of around 50 minutes, and then the area increases and decreases in size, and then it dissipates. So these are the summary and conclusion. So first, the study uses a TOBAC for tracking mesoscale convective cells using Tulse radar observations. It is observed that the highest number of cells has a lifetime of approximately 1 hour, that is 60 minutes. Cells with longest lifetimes, 150 minutes, were the fewest, just numbering less than 20. Similarly, maximum number of cells has a velocity of less than 25, that is approximately 24.5 meter per second. And very few cells had less than 20. So very few cells, like less than 20, had a velocity of greater than 40 meter per second. So thank you, and acknowledgements for respond, VSS ISRO and MOES NARM.
Yeah, we can take some questions. Yeah.
Thank you for your nice presentation. I just wondering, you are showing initiations and your dissipation. So that is starting like from 18 kilometers square?
Yes, sir. So for this cell, it is starting from 18, so the area, 18 kilometers square.
No, this is the area, right? So it's like initiating and mature and then suddenly dissipating.
What is the minimum area that you decided to define a cell?
Sir, basically the segmented value.
What is that? What is the minimum value when it is considered as a cell?
So we will have the features about 30 DBZ values.
That is a reflective. What is the area that it should attain to consider it as a cell? So what is the threshold area value?
So we have threshold in terms of reflectivity values.
Now, once you identify a feature, it should have a certain, otherwise you will be counting just noise. It should have certain area. Na? And what is the duration, minimum duration that a cell should have? Then it will be called as a cell.
Basically, you have to look at
threshold.
Area or volume, one of the two. Anyway, that you can consider.
Sir, so in this case, what we had
it has there in the software.
So it's something like that you consider the graded data product and one pixel, if it is more than 30, you consider that as a your cell, right?
So how many connected pixels should have to qualify it as a cell? That is the minimum area. Okay. Please consider that. And
sir, like area is like whatever is about 30 DBZ. In my case.
Okay. Thank you. Okay. 1 pixel only. Okay. So number of pixel, yeah. So we conclude this session, and then for the next session, please invite.
We thank Professor J.S. Bhatt and Dr. Sachin Deshpande for chairing the first oral sessions of the day. Thank you so much, sir. We will now proceed to the final oral session of iRAD 2026, and I request Professor Dr. Subrata Das and Dr. Takashaki to chair the sessions, which is entitled as Microphysical Studies and Dual Polarization Observations. This is, I guess, part 2 of the previous session. So we will start with the session, sir. Over to you.
Hello. Yeah. Good afternoon, and actually good noon. And we will again back for the second part of this session on microphysics, and I think this is the last session for this iRAD 2026. So with that, not taking much of the time, I would like to invite Dr. Aishwarya, and she will be talking about retrieval of maximum probable haze size using spectral polarimetry from C-band dual polarization Doppler weather radar observation during Relampago field campaign. Yeah. Aishwarya, yeah. So Aishwarya, please stick to the time so that lunch should not be delayed. Thank you.
Good afternoon all. I am Aishwarya Lakshmi from Indian Institute of Technology, Palakkad. So today I'm here with a discussion on the retrieval of maximum probable hail size using spectral polarimetry from C-band dual polarization Doppler weather radar observations. So this is a collaborative work between IIT Palakkad and the Colorado State University, and I would like to thank Professor Chandrasekhar for providing us with the Relampago data. So let me begin by discussing the motivation and objectives of our work. So the accurate determination of hail size distribution in a convective storm is important for the nowcasting and forecasting purposes, as well as to study the hail size, to study the microphysical properties and the dynamics in a hail region of the convective storm. So the hail size distribution parameters can be determined and studied using the polarimetric measurements from a weather radar. So however, the spectral polarimetric variables that combine the Doppler and polarimetric measurements from a weather radar can also be used to determine the particle size distribution in a hail region. So in our study, we have used the spectral variables together with an optimization framework to determine the maximum probable hail size. So we have used data from CSU Chivo AC band dual polarization Doppler weather radar from Colorado State University, which was deployed during the Relampago field campaign. Now let's look at the characteristics of polarimetric variables during this convective storm, which is well characterized by the high values of reflectivity that can be seen in the top left figure here, which is reaching up to 60 dBc at 40 kilometer distance from the radar, extending to an altitude of around 12 kilometer, and there is a corresponding CDR column in the top left, top right figure, and a lowering of copolar correlation coefficient that can be seen in the bottom left figure. Having looked at the polarimetric variables, now let's look at the spectral polarimetric variables, which are derived by applying an FFT on the autocorrelation of IQ voltage sequences from the radar receiver, which derives the spectral variables, namely spectral differential reflectivity SCDR and S-ρHV, which is the spectral copolar correlation coefficient. So we have looked at the hail region, which can be seen in the hydrometeor classification here, located at a 40 kilometer distance from the radar, extending from 5 to 7.5 kilometer, and the spectral variables, namely the spectral reflectivity that is shown in the left column in the right figure, and the spectral differential reflectivity in dB that is shown in the right figure, are derived for this hail region. We can see that the spectral reflectivity shows a broad flat-topped spectrum at all the altitudes where hail is present. So together with the measured spectral reflectivity, we have formulated a spectral reflectivity model using the particle size distribution N of D and the backscattering cross-section sigma HH. And we have used an empirical relationship between the terminal fall velocity and the diameter of hailstones, which is shown in circle here. And this product of particle size distribution and the backscattering cross-section is convolved using a Gaussian kernel that incorporates the effect of turbulence on the spectral reflectivity. And the sigma naught parameter of the Gaussian kernel represents the total spectral broadening. Now let's look at the retrieval algorithm. Where we have derived the spectral reflectivity from the IQ voltage sequences from the radar receiver, and the optimization framework minimizes the difference between the measured and the modeled spectral reflectivity. And the parameters optimized here are the slope parameter, the intercept parameter NW, the shape parameter mu, and the slope parameter lambda of the particle size, a gamma particle size distribution, and the backscattering cross-section sigma h comes from the T-matrix method. So here shown are the spectral reflectivity model with the optimized parameters from the retrieval algorithm at the altitudes where the hail is present. The parameters of goodness of fit shows that both the modeled spectral reflectivity from the optimized parameters and the measured spectral reflectivity shows a very good fit. And the particle size distribution, that means the hail size distribution, thus retrieved for the hail region are shown here, which shows a diameter range or maximum probable diameter range between 4 to 12 centimeter diameter. So an uncertainty analysis is performed on these parameters of hail size distribution, optimized hail size distribution, and we have identified the mode diameter as the diameter that maximizes the product of backscattering cross-section and the particle size distribution. So this is considered as the maximum probable hail size, and at a 5 kilometer altitude, we have found that the mode diameter, which is the maximum probable hail size, is 5 centimeter, and a full width of maximum range represents the maximum probable hail size in the radar resolution volume, which is ranging approximately from 4 to 8 centimeter diameter. So here shown are the images of hailstorm collected during this convective storm event, and this shows hailstones of approximately 8 centimeter diameter. So let me conclude my talk by mentioning the significance of this retrieval framework. The spectral polarimetric variables, we have seen that the spectral polarimetric variables provide information on both the backscattering properties and the terminal fall velocities of hailstones. Therefore, this represents both the hail microphysical properties and kinematics. Therefore, the retrieval framework that uses the spectral polarimetric variables capture the full complexity of the microphysical and the dynamical processes within the convective storm. So this offers a more physically consistent method for the retrieval of hail size distribution in a convective storm. So these are the key references. Thank you.
Thank you very much for nice talk. So any question? May I ask one question about that? So after you estimated hail size, diameters, can you plot the hail size in the RHS scan plot?
I didn't get your question. Can you please repeat?
After you calculated the hail size, diameter, can you replot again the hail size in the RHA plot?
That means the vertical distribution?
Yeah.
Like I have shown a plot here. So this is the particle size distribution for the different altitudes in the hail region.
Yeah.
Okay.
If you...
Yeah. This one,
so
right?
you are only, focus on that area. Okay.
So this is the hail region from the hydrometeor classification, which is at 40 kilometer distance from the radar.
Okay.
So I have shown this encircled here, the hail region, which is from 5 to 7.5 kilometers of altitude. So the size distribution is retrieved for these altitudes.
Okay, thank you.
So,
So can you calculate some melting processes of the hail?
Melting process, we have means in the spectral reflectivity model.
Yeah.
So we have used the T-matrix method for calculating the backscattering cross-section.
Right.
There we have considered to represent the dielectric properties, we have used that effective model approximation using the Bregman's rule. There we have considered the presence of water too.
Okay. So, thank you.
Yeah.
Thank you, Dr. Aishwarya. And now we will go to the next speaker is Dr. Tamin Sarkar. And he will be talking about study of hydrometer classification algorithm using Bayesian approach for S-band polarimetric Doppler weather radar.
Hello, good afternoon everyone. I am Tamin Sarkar, and today I am going to present the study of hydrometer classification algorithm using Bayesian approach, and it is the study is mainly used for the Cherrapunji S-band Doppler weather radar and my co-authors are Abhay Srivastav and Shyam S. Kundu. So the outline includes the introduction, the basin hydrometer classification, the radar variables, analysis results, conclusion and references. Now the Cherrapunji Doppler weather radar is situated in one of the world's weightiest places. It is operating at a frequency of 2.75 gigahertz and it is at a height of 1,484 meters and it has been in operation since 2017. Now coming to the basin hydrometer classification, we have used 8 hydrometer classes which are considered as hail, rain, gropal, crystal, wet snow, biological scatter, ground clutter. So for our study, like 5 radar variables was considered as input as was taken by the reference 1. So coming to the basin theorem, actually it consists of the class variable Ci and a vector of observed variables. So which states the theorem as the conditional probability is equal to the product of the prior PDF and the conditional probability density function. So now mapping to the hydrometer class and substituting to the basis theorem, it leads to equation 1. So in which each variable Vm is independent of Vn. So as a result, the P of Vi to V5 is assumed to be constant. So finally that equation 1 is transformed into this, which leads to equation number 2, where SFI represents the scaling factor, which is a factor which depends upon the various radar variables. Now the conditional PDF and prior PDF are the crucial components in the basin classifier. Now advantage of basin classifier is that it requires small amount of training data for the construction of PDFs, and the PDFs for each variable needs to be modeled before applying them to the VSCA. So which shows different shapes. So as you can see in equation 3, 4 and 5, where 3 represents the negative skewness, 4 represents the positive skewness and 5 represents the Gaussian shape. And A, B, C, D are the fitting parameters which are mainly determined by using the nonlinear least square method, curve fitting method. So based upon that, from figure 1 you can see the CL-PDF functions are fitted based on the equations 3 and 5 for ZH, rho V, SD ZH and SD phi dp. Now for the BSCA methodology, we have also compared it with the Marzano basin hydrometer classification method. Now in our case the 8 hydrometer classes are used, but in Marzano basin hydrometer classification 8 hydrometer classes are used. So what we did, we combined the 3 large rain, medium rain and heavy rain to rain, and also the rain and hail mixer to hail. So we have taken a particular date of 1st June 2025 in which it is considered as a heavy rain or thunderstorm probability in the region of Silchar area. So 4 elevations are taken. Now these are the differential phase shift plot for the 4 elevation angles and the correlation coefficient. Now as we can see from the basin hydrometer classification plot, it actually able to identify the hydrometers at each of the angles 1 degree, 5 degree, 12 degree and 18 degree. But in MBSC method is not able to identify properly. For the BSCA method, actually it uses some additional input variables like the correlation coefficient and standard deviation, which is able to accurately identify the hydrometers, like even clutters, and also it can easily identify. So for comparison, we have used a confusion matrix. So in that matrix, we can say that for the MBSCA, mostly the hail, it is the value is 85.4%, which is accurate, and for elevation angle 18 degree, also we can see that the MBSCA, it can closely match with the true value, that is the predicted value of BSCA, 48.2%. Now we have also shown a bar plot which shows the accuracy for the two elevations, for elevation of 1 degree and 18 degree, in which we could see that the MBSCA, it matches with the basin method with the accuracy of 80%, and for hail, and the rest for rain it is 30%, and similarly for 18 degree elevation also, the hail it's able to identify, that means the MBSCA method with BSCA method, the accuracy of 45%. Now for the conclusion, mainly the method that we have used, it's because of its uses some additional radar input variables, it's able to provide substantial information about the biological scatterers and ground clutter, which is not provided in the Marzano method, which we have compared with. So in future we'll be using some additional hydrometer types so that it produces robust BSCA. These are the main references used. Thank you.
Thank you. I have just one quick question. What is your ground truth for comparison? Like you say accuracy, what is your ground truth for your accuracy estimations and other things? Means you said accuracy, right? Means you have compared with someone, right?
Yeah, actually sir, we have directly compared the method of Marzano and that basin method of the young which you have used.
So that is a comparison, right?
Yeah,
Not
yeah.
Okay. Yeah, time for the questions. Okay. Okay, thank you, Dr. Sarkar. Let's thank the speaker. And let's move on to the next speaker, Dr. Manisha. And she will be going to talk about ZDR columns and lightning activity, insights into the convective storms of drafts.
Good morning, everyone. Myself, Manisha Tupsondare, working as a project scientist in Indian Institute of Tropical Meteorology, Pune. The topic of my today's presentation is ZDR column and lightning activity, insights into a convective storm updraft. Here, I would like to thank all the co-authors listed here. So the background or motivation of my work is that the deep convective clouds they found in the tropics as well as in the mid-latitude, they plays a key role in the Earth's energy and water budget and the climate systems. They forms when warm, moist, unstable air rapidly rises and forming a strong vertical current that drives the thunderstorm. In the atmosphere, these deep convective clouds occurs in a small scale as isolated deep convective cells, or they occurs on a larger scale or more organized scale, that what we call as the mesoscale convective systems. So studying these clouds, their structure and evolution, that helps to understand the convection role in the weather and climate. So what are these ZDR columns? So these are the vertical regions of the enhanced differential reflectivity that are exceeding above the freezing level, which are indicated by the large supercooled droplet lifted by the strong updraft. They act as the early precursor to the severe convective development. So these increasing column height that signals the intensification of storms. So Brandes et al. 1995, they mention that these ZDR columns were influenced by large liquid drops and the mixed phase precipitation near their tops. Whereas Herzberg et al. 1992, they showed that in the mature cell of convective cell, the polarimetric signature of both hail as well as heavy rain, they following the appearance of ZDR column. So these columns, studying these ZDR columns were useful for nowcasting, storm life cycle monitoring, and short-term forecasting. So objective is to detect and identify the ZDR column using polarimetric radar observation to identify strong updraft and relate their features to the cell intensity and evolution, and to provide early indicator to the storm development through high-resolution ZDR column monitoring and enhance nowcasting and short-term forecasting for the convective cell across the India. So, we all know that during Indian summer monsoon, there are three strong convective monsoon zones. So Western Ghat, Northeast India, and the Central India. So over the Central India, the large-scale synoptic scale system, for example, lows, depression that forms and moves in northwest direction, which produces heavy precipitation over the Central India. So IITM installed CPOL radar over this Central Indian region. So I use this radar data to track the convective cells. Next, to understand the relationship between the polarimetric variables and the electrical activity, so we use the lightning data. Next, the ZDR column of convective cells was identified to compare the microphysical characteristics of convection. So for that, we have used a threshold of reflectivity 10 dBz, and differential reflectivity should be greater than 2 dB, and its vertical extent should be 500 meters above the freezing level. So this is the method that we use for the identification of convective cells. So these are the properties, like month-wise properties of the convective cells during JJS 2023. So we can see the convective frequency of occurrence of convective cells. So this convective initiation shows month-to-month variability. July month shows the maximum number of count, whereas August month exhibits lowest initiation counts. Like here also we can see in the box whiskers plot of area, reflectivity, and maximum 20 dBz decodified. July month shows relatively deeper and intense convective cells with the wider areas. Diurnally, if we see the prominent peak in the diurnal cycle of this cell initiation number, which is centered at around 15 local time, and with a weak nocturnal peak is observed in 2 to 4 hours. So this is the vertical structure of convective storms. Here we have taken two cases. First is from 10th August 2023, and second one is on 19th August. So this animation shows the reflectivity and ZDR for that identified cell. So this black spot on this ZDR that represents the identified ZDR column. So in this both we can see the, in 10th August case, we can see the reflectivity, like weak disorganized reflectivity that consistent with the shallow and short-lived convection. These low values of ZDR that indicate small hydrometeors and limited microphysical variability that are the characteristics of suppressed convection, whereas for this case, in the mature cell, we can see the multiple ZDR columns. So next we have plotted the number of ZDR column and at what height they are reaching. So for this case, we can see the fewer or lower number of ZDR column that are reaching up to 8 kilometers. That indicates the weaker updraft or the suppressed convective activity, and that reflects the mixed phase development, limited mixed phase development or minimal hydrometeor growth. Whereas for this case, the higher number of ZDR column that reaching up to 14 kilometers, that indicates a strong updraft and a deep convective development. And this column that extending greater than, we can see 6 kilometers, so that indicates large size particles due to the strong updraft. The increased column frequency and the vertical extent suggest that the vigorous microphysical activity and enhanced mixed phase processes that consistent with the deep convection. So overall, this observed variation of number and height of ZDR column effectively captures the dynamical evolution of convective storm phase that are linking with the microphysical structures with the electrical activity. So these results are important in monitoring the ZDR column characteristics as an indicator of storm intensity and electrification potential. So next we have taken a special case like MCS. We also identified this ZDR column in the MCS case. So this is one example of MCS that are observed during 6 to 7 July 2023. This is the MCS precipitation during that track. And this life cycle of MCS divided into convective, stratiform, and anvil region. So at the mature stage, we can see a squall line structure. If we take a cross section of this, we can see the trailing stratiform and leading convective line. So this is the life cycle evolution of that MCS and the storm properties. So we can see in the mature stage of the MCS, both cloud and core area shows a maximum. During that time, the number of convective cores are always that also maximum. So these areas of most intense convective features is positive ZDR value that increases through the convective initiation to the mature stage. And as this MCS matures, the increase in the updraft strength and the special extent that leads to the high positive ZDR and KDP values. So this is the QVP of that. So this combined use of KDP and ZDR volumes above the melting layer that provides a proxy for the deep convective updraft. So here we have taken a KDP volume above the melting layer that we can see that remains elevated during the mature stage of the MCS, and it indicates the increased deep convective characters of the storm structure. Whereas ZDR volume, if we see, above the melting layer, we can see it has increased before these elevated positive values become evident. And these findings are agrees with Bringe et al. 1996, which shows the use of ZDR column as an early observational signal to the deep convective updraft. So next we check the relationship between this lightning count and ZDR and KDP volume that reveals signals, polarimetric signals associated with mixed phase processes in deep convection updraft and the lightning. So we found a strong correlation between this KDP volume and the lightning count. So this is the summary. So
okay, thank you very much. Any questions? Okay, so I have a question about ZDR columns. Have you analyzed a kind of dual Doppler analysis to estimate the vertical air motion on this case?
Can you please repeat the question?
Dual Doppler analysis.
Yeah, it is dual.
Dual Doppler analysis? No.
This is
to estimate the vertical air motion.
No, sir. He has not considered.
Okay.
He has just considered the polarimetric signature to understand the microphysics. So what you are suggesting, like the large scale, the wind pattern, another kind of the dual.
Okay, understand. Yeah. Okay. And I'm curious about the relative location of the ZDR column of each convective cells. Have you tried to see that kind of stuff?
Yeah, we have checked the location of ZDR column with.
So the.
This is the ZDR, like black spot indicates the ZDR column. Here we can see this is just a one time step where this black indicates the location of that ZDR column.
I think in the next plot, you have the evolution of the cell.
Yeah, here we can see the evolution of ZDR column. Like how many ZDR columns and at what height they are reaching.
Okay, thank you very much. Okay. Any other questions? Okay, thank you.
So we will move to our next speaker, Abhishek Jha, and he is be talking about modulation of storm scale convection over the monsoon trough region by monsoon intra-seasonal oscillation.
Yes. Thank you, sir. So, good afternoon, everyone. I'm Abhishek Jha. Today I'm going to talk about the modulation of a storm scale convection over the monsoon trough region by monsoon intraseasonal oscillations. This work has been carried out as part of my PhD thesis under the guidance of Dr. Subrata Das. Before going to talk about the findings and how these large-scale features propagating monsoon intraseasonal oscillation shapes the convection over the localized region. I would like to give a brief background meteorology of the monsoon trough region. As in the previous talk, also Manisha shown that over this region, LPS generally forms and propagate westward. This figure here, this is 500 HPA geopotential height contours overlaid with the setting as a topography, and here this color bar represents the moisture content, and this is LPS frequency. From this you can see that this provides a synoptically active environment, a number of LPS form. For storm scale convection we have used radar observations, and for large scale features we have used radar 5 and other satellite products and other reanalysis products. So our radar sits here, this is S-band Doppler with the radar, and over this region, especially this is a very good test bed to conduct this kind of work, because most of the LPS forms and propagates through that. Also, other than the monsoon, different systems form over the Bay of Bengal and passes through that. Overall, this vertical structure of the region, if you see two types of thermal environment we generally observed, which one is the cold core during the monsoon season. These LPS are basically cold core systems, and in the pre-monsoon and post-monsoon we have frequent tropical cyclones forms over the region. Due to this, the environment also you see this completely warm core structure over the region. So this type of thermal structure that creates synoptic environment over the region, and that's accompanied with the large scale convergence features over the region. And then storm scale convection over Indian region has been very sparse. Very few studies has been done in the previous works. Most of them were limited to the few case studies. For example, this Utsabal, they conducted their work on the Western Ghat. And monsoon trough, one very important study done by Sindhu and Watt, but still those were given based on some specific number of observations, and Doyle et al. They also looked into some statistics of the cell specs, but those were also limited to few cases. Here we will be using 12 years of data set to analyze this. 9 years of radar data, S-band Doppler with the radar data we have used for this study, and those routine calibrations were done by IMD for data quality check. Overall, we have used, this radar has a specification of 10 elevation from 0.2 to 20 degree, and generally it scans in the 7 minute and 10 minutes resolution. In previous talks other speakers have shown the specifications of the S-band weather radar, so I'll skip it here. And overall, we used data, and then we did quality calibrations, QA/QC, compared against the spaceborne radar. Then we used a space track algorithm, which is Titan, and then this criteria we have used 35 dBg reflectivity in a contiguous volume of 30 kilometers square, and then those has been tracked in space and time, and further other parameters of kinematic and dynamic are explored, and then it is like thermodynamic and other parameters have been extracted to. This is the monsoon intraseason oscillations indices has been reached from the Airbus IATM, and this is the 8 phase evolution of the geopotential height. From this you can see that, and these are right panel is the 8 phase evolution of convective storm frequency derived from the S-band Doppler weather radar, and from this you can see that phase 3 and 5 are associated with the more number of frequent LPS, frequent storms. But again, the MESO is a very large, spatially organized system. When it passes through our region, these phases may or may not be the sufficient, because convective storms has a life cycle of 1 hour or less. So we need to redefine these features on our region. So for that, we tried, since this is north of the 20 degree latitude, so we speculate there can be this quasi-geostrophic approximation can be valid. For that, we first checked the necessary conditions, which is very less, this Rossby parameter should be less, and also beta plane approximation should be valid. Based on that, we using the 20-degree north latitude, also the mean characteristics of the length and mean winds value we calculated, and this is basically applicable. And I'm not going to the details of these equations. We further analyze the quasi-geostrophic vorticity equation, which is omega equation, and also the this height tendency equation. Based on this, if you solve these equations by considering this meso as a horizontally propagating convection in terms of wave structure, and you put these standard wave equation formula in this, so you will come to that it comes as a these terms will come as a Laplacian of any quantity. It can be whether it can be geopotential height or any dynamic variable. It is proportional to itself like the vorticity advection and temperature advection terms. Further, if you solve this will come in the form of vertical velocity and static stability in terms of the advection and temperature advection and differential vorticity advection. For a given forcing, let's say in a particular phase you have a constant this forcing advection, this vertical velocity will be inversely proportional to static stability. So whenever there will be some convective features, this way it can force the localized convection. Further, we also check the so this parameter Laplacian of any dynamic variable can be used to see whether these just I will take few minutes. When it propagates through your region, whether it forces convection localized, so it can be used as a proxy. So we use this proxy, and other variables we also analyzed, and we saw that during enhanced and suppressed meso, we categorized into enhanced and suppressed meso, and these enhanced, the third, fifth, and eighth phase come under the enhanced phase, and others are in suppressed phase. In enhanced phase, obviously there is a large convection number of frequent convective systems. During suppressed condition, relatively less, but still there are number of storms. So I will be showing why it does so. For this is the vertical structure of storms during the enhanced and this suppressed condition. You see, during enhanced condition, you have larger ecotop height as compared to the suppressed in general, and those are also short-lived, longer lived in terms of lifetime. So overall, these are like large, deep, intense, and long-lived systems. However, during suppressed condition, smaller and shallow, less intense convection, those are shorter lives. So to understand this, what could be the possible mechanism behind that? So we tried to look into barotropic and baroclinic instability. This is the background wind and moisture. You see a large gradient that can give. So these systems basically draw energy from the background state. These are the perturbed state in terms of baroclinic instability, and also in vertical, a large vertical velocity gradient. Wind shear you can see. Also this is like spatial distribution. You see the large gradient in the wind shear. So overall, during this enhanced condition, more number of LPS, as in the previous work done by the Goswami et al. And also Karmakar et al. They saw that during the positive, active phases, more number of LPS are formed. So those create synaptic environment. Also, this meridional gradient in the mean moisture and wind perturbation can give the energy to sustain those large those systems.
Abhishek, please wind up.
I'll wind up. And also barotropic instability in the horizontal will provide the energy for the sustainability of these systems. We also observed that some system could develop due to, even though it was synoptically unfavorable during the suppressed condition, still there were some systems, those were deep and intense. So we tried to analyze the effective stability, but since these are the moist convection, we tried to look into the moist effective stability based on the Gorman et al. And we could found that during the suppressed phases, those systems were facilitated by the reduced effective moist static stability. And we speculate this could be due to the diabatic heating produced by the CS scale convection. Thank you.
Yeah, thank you, Abhishek. Now time for one quick questions.
Okay.
Thank you very much. Could you tell me the enhanced and suppressed phase, how the ratio of the convective and stratton precipitation?
So here we completely tried to look into the convective features. Well, definitely we can quantify even what is the ratio of convective and stratiform.
Even the suppressed phase, you have shallow convective systems, you mean that?
So, during suppressed we have shallow convection, and generally overall statistically during suppressed we have larger number of shallower system. Enhanced we have larger number of deeper and more like long-lived system. But even during suppressed also we have some number of system that could grow into the deeper and intense. So we try to look what could be the possible reason behind that. So we could find that this moist effective static stability was reduced during those conditions. If you look into the vorticity advection equation and height tendency equation, so W is inversely proportional to 1 by this is alpha. So and also if you try to analyze the vertical velocity, even though we did not have observation, we tried with ERA 5 data. So even though the whole atmosphere was lifting up with some positive velocity, within that we have a localized downdraft. So those downdraft could be associated with the CS scale convection, and that could produce the diabatic heating that may further feedback the instability to grow these systems, since these systems are very localized.
Okay, thank you. Okay, thank you very much.
Thank you.
So the next speaker is Prakash Naik, and he's going to talk about advancing cloud and precision microphysics through optimized Doppler velocity unfolding as a CPR application with extreme rainfall case study.
Hello, good afternoon, one and all. I am Sheikh Bakash from Kyushu University, Japan. Today I am going to give my presentation on advancing cloud and precipitation microphysics through optimized Doppler velocity unfolding and healthcare applications. You can see these are my co-authors. Yeah, this is outline of my presentation. The introduction, I will describe what I am doing here, and then in the system description, velocity folding, that is one time fold, two time, and so on. Then finally, healthcare CPR applications. Finally, the summary and conclusions of the study. Yeah, one can ask why velocity folding is required. What is mean by, first of all, velocity folding? As we know that any radar, you can see it can transmit the signal, and then there is a target. It could be the cloud or precipitation, whatever it is. We can receive the that is reflected signal, and this reflected signal consists of the it could be the reflectivity or Doppler velocity, and this Doppler velocity, especially for the radars, the Doppler velocity exceeds the Nyquist velocity. That means unambiguous maximum range of that velocity. It could be exceeds that Nyquist velocity. At that time, we may obtain the folded velocity. It could be also called as the velocity aliasing effect. This is the what will happen, why we need to do, in the sense you can see here the Doppler velocity, the folded Doppler velocity may look like there are erotic velocity. That means it is kind of folding effects is there, but if we do unfolding, we can see the smooth profile. So why it is required? For example, if there is a folding effect, there is a misidentification of the winds, then in a similar way, the precipitation is also, the precipitation types is also misinterpreted. Then due to this folding effect, we may not obtain the true wind shear. And this is due to the type of precipitation, that means whether it is graupel or raindrop, it can be misinterpreted. That is the problem. This is the system description. Initially, this methodology is applied for the high resolution, high sensitivity W-band radar, and then it is applied to the earthquake CPR. Of course, the earthquake CPR consists of the ATLID, that is LiDAR, Doppler LiDAR, as well as the earthquake CPR, cloud profiling radar, and then this is broadband radar, and this is multispectral imager. Of course, in this in this presentation, I would like to describe only the CPR products. Of course, this is the track of the earthquake CPR. We may have the different type of earthquake products. Of course, you can describe. This is my team members, my team leader, and then core team leader. And this is the HC Spider specifications. This is high sensitivity radar. That is at 15 degrees, we may obtain the minus 50 dBz. This is a velocity unfolding methodology. Of course, why it is velocity unfolding required? One can ask, okay, there are velocity folding methodologies are there, why it is required? For example, the existing method which is using only the fixed the threshold, that is 3 meters per second. Sometimes it could be work, sometimes it may not work. Why? Because, for example, there is high convection is there, so the Doppler velocity may increases above 3 meters per second, but at that time this methodology may not work. That is why we calculate this new methodology, we propose this new methodology, which is purely dependent on the relationship between the Doppler velocity and then this reflectivity. So initially we calculate the gradients and then normalize these parameters of reflectivity and Doppler velocity. Then trend has been calculated based on the Doppler velocity and reflectivity. Then finally we have proposed a threshold based on the empirical analysis. Finally, this velocity folded pixels has been identified using this threshold. The folded pixels has been corrected. So this is the one of the example. You can see this is the normalized velocity and then normalized reflectivity. The original velocity, you can see there is when there is a updraft, when there is a drastical change in the Doppler velocity, it may indicates the folding or the aliasing effect. You can see there are abrupt changes. These abrupt changes indicates the velocity folding. So in this methodology, the gradient and then trends have been identified, calculated. So finally, this is conventional methodology. As I said earlier, this conventional methodology only depends on the fixed threshold, that is 3 meters per second. It can remove up to some extent, but whereas here it is below the 3 meters per second, but it is folded velocity, it is not corrected. But whereas our methodology, it can able to correct completely compared to the conventional method. So how we have used these thresholds, that is based on the empirical analysis. We have taken different type of velocities, and then we found this 1.6 threshold is the suitable one. You can see the folded and then unfolded and then unchanged one. It is clearly classifies the folded and then unfolded pixels. So this is one example. You can see this is the folded Doppler velocity, but whereas the Doppler LiDAR shows there is a negative, but whereas it is positive. However, it has been corrected using the proposed method, but where the conventional method, it has some residual folding pixels. So finally, we obtain the good correlation. This is for one day data. You can see good correlation compared to the conventional method. This is for 1 year data. You can see the good correlation is very good, and then root mean square error is also low compared to the conventional method. And it has been applied to the earthquake CPR. You can see here, this is the folded pixels. There are folded pixels are there, whereas the conventional method that is, which is depend on the only the fixed threshold, it can able to remove some up to some extent, but whereas it has some sort of folded pixels. And then the standard method, this is the conventional method, this is the standard method which is using right now in the earthquake CPR. It is also removes some sort of the signal, but some above the melting layer there is some sort of folded pixels is there. So but whereas the proposed method it can able to remove completely. You can see clearly distinguish between the standard and then proposed one. These are the Doppler velocity and then reflectivity relationships as well. So that is one folding. For example, there are multiple foldings. What will happen? So at that time, we proposed a methodology that is totally dependent on the microphysical characteristics of various type of regimes, that is clear cloud and so on. So you can see there are different type of folding effects over there. Finally, we can able to find different kind of foldings. So this is the perfect model, suitable model we have selected, and this model has can able to fit this only the true velocities. These are the different type of folding effects. You can see 1-fold, 2-fold, 3-fold, and so on 5-fold kind of things. Finally, it has been corrected. This is the corrected Doppler velocity and then reflectivity. So this is one of the case. You can see the proposed method can able to work perfectly compared to the standard method. Thank you.
Thank you very much. So, questions? Yes. Yeah.
Oh, okay.
Yeah. So now the CPR is operating. Yeah. And he has to mention about holding velocity is about actually 5 or 6 meter per second, depending on the PRF. Actually, it ranges from the 6,500 hertz to 7,000 hertz. Right?
Yeah. Yes.
Yeah. Okay. Any other questions? So, by the way, so holding events occurs for the weaker Z region.
Yes.
How do you treat with that? Similar approaches are available for you?
Yes, this approach is working for those cases also. I didn't show. I have taken one clear case. There also, as we know that the folding effect we have observed, and this methodology due to the reflectivity and velocity relation, we have given more weightage to the reflectivity. So due to this more weightage to the reflectivity, it can able to detect those folding pixels as well in the weaker section also.
Okay. Okay, thank you very much.
Thank you.
And next speaker is Mahen Kaur, and title of his presentation is Cloud Microphysical Processes of Producing Convective Clouds over Northeast India, Insights from In-situ and Twin Observations.
Yeah, good afternoon, everybody. So myself, I'm going to talk about some cloud microphysical processes of that produce lightning strikes over the northeast India, and we had actually luckily in situ measurements by aircraft, and of course we also had some trim pass. But this is a background. You can see Northeast India is second to none in terms of producing lightning strikes, and actually this is one of the global hotspots of lightning. And it was published in the year 2020 in QZ. You can see that these clouds can be developed up to cloud top can be minus 70 degrees centigrade. That has potential of producing a lot of lightning strikes. So, but then, so what can be the fundamental reasons behind these lightning strikes? Because the lightning strikes, if to be there in that convective clouds, it should have groupel and supercool water coexistence of those hydrometeors. And we hypothesized that because we had a lot of moisture budget in the Northeast India, if the liquid water content is quite high, just below the 0 degree isotherm, and if they go to the colder stage, and actually supercool water can exist, and because of the biological aerosols or say some ice nuclei particles, probably mixed phase precipitation actually occurs too early in these clouds. And when they form those mixed phase hydrometeors at a kind of warmer temperature, say -1 to -2 degree, because of the surge separation, and because we have a lot of updraft in these clouds, and these lightning strikes could be produced. So I will basically talk about some general structure of the storms as we studied from the TRIM PR. And then we'll try to establish relationship between the aspect ratio, diameter, and try to understand the change in the droplet size distribution. And also we'll try to establish a new autoconversion rate because this autoconversion from, say, cloud droplet to raindrop will be very, very critical in these lightning producing clouds, because the drizzle formation, or say liquid drops, actually determine the this surge separation processes here. So this is one of the I will say kind of very lucky to get this flight. We took this flight back in the year 2009, 6 September. You can see, yeah. So this actually black line shows the aircraft pass that the Guwahati air. Yeah, so we took off and we took measurements of convective clouds that was actually freshly developing, and these are the strikes of lightning. Then this cloud actually, when you take kind of intersection of these clouds, they actually lifted up to 15 kilometer, and we had a lot of higher DBG values, but we don't know when, we cannot correlate with lightning strikes with these DBG values. So if we study this, actually we had another cloud pass on 4th of September, cloud profile. And if you see here that the interesting factor here is at -2 degree, these are super cool water, then you have the gropels and some high, even say some ice particles, newly formed ice particles in -5. So you have a lot of mixes particles at this warmer temperature. So if we plot the vertical profiles of the cloud droplet concentration, then LWC, yeah, what's the extremely high values of ice water content, then you have a lot of LWC. For example, here it is nearly 2.5 to nearly 3, and then drizzle actually form here, somewhere here. This is the critical radii where you have the drizzle formation in the clouds. So we also calculated the autoconversion rate in these clouds, and these autoconversion rates actually are maximum when you have the drizzle formation, but you have some ambiguity here, and maybe because of the depletion of the small drops, you know, you have the decrease in the autoconversion rate. So finally, we also established the relationship between the axis ratio and the diameter that can be used in the models. And you see, if you see the blue colors, they're in the negative temperature, you have a lot of ambiguity here. They actually don't follow this relationship, but maybe we have to, but we considered all the drizzle drops and cloud drops. And on another important factor, when you study the normalized gamma drop size distribution, we have two clusters here. One for cloud regime, then one for when you have formation in the cloud droplets. When you have actually mu values, shape parameter of the gamma drop size distribution, that's approximate to 0 or say a little bit of negative values, you have very, you have a separate cluster here. So this parameterization actually can help to automatically segregate the cloud regime and the drizzle form regime also. And you can see the shape becomes concave upward when you have the drizzle formation, because you have dominance of collisions process here. And then we try to understand, how this autoconversion relationships, say for example, this KK2000 and Lean down, they fit into our region. Then we found they're actually far away, and this actually emphasized that we should have region-wise or say environmental-wise autoconversion relationship everywhere in our Indian subcontinent. Yeah, thank you.
Mine?
Yeah. So, yeah.
You said that there is a high amount of LWC just beneath the melting layer. That could be the reason for the lightning, because it produces more mixed phase hydrometers. Have you also explored the updrafts measurements from the aircraft for that particular case?
Yeah, that Ames probe had some problem, so we are not using the updraft data here.
Okay.
But we had nearly 1,000 feet per meter.
So, in absence of that, what could be the reason for having the high LW? Because how frequently the high LWC presents near the LWC, near the melting layer? Because if that is the main hypothesis for having the mixed phase hydrometers and the lightning.
Yeah, but the hypothesis is that if you have lot of liquid water content just below the 0 degree isotherm, that actually kind of fueling the formation of supercool water. So when you have supercool water in the atmosphere, and then if you have the ice nuclear particles, for example, pollen grains here, bioaerosols, they act as ice nuclear particles. So that actually they can form ice particles immediately at very, say -1 to 2 degrees centigrade. So they automatically form kind of mixed phase cloud here. So, but then we are setting up new experiment here to study these processes.
Okay, thank you.
Any other questions? Okay.
Just wanted to know whether any sensitivity studies have been done in this aspect.
Yeah, that we are looking forward for WRF. We will replace the this KK algorithm with our newly developed one, and we'll see how they perform. Yeah. Thank you.
Okay. Thank you very much.
Thank you.
So the next speaker is Samesh RK, and assessment of GPM DPR observation of warm rain microflakes over the Western Ghats using multi-year micro rain data profiles.
Yeah, good afternoon all. I'm talking about the assessment of GPM DPR observations over the Western Ghats with the ground observations. So, these studies have shown that satellite-based observation over a complex terrain have systematic biases because due to the underestimation of orographic and warm rain. Okay, so since the warm rain are characterized by shallow vertical extent and weak reflectivity aloft, and it's raindrop growth below the 2 kilometer. So, but studies by Piano et al. 2024 and Spears et al. 2016 shows that the DPR GPM detects the warm rain aloft reasonably well, but mixes a smooth, intense, low-level rain. So with this motivation, we hear that how well this GPM DPR represents the near surface rain rate and vertical reflectivity structure over the complex terrain of Western Ghats. So we have taken the study area of our high altitude cloud physics observatory, which is at 1,820 meter above mean sea level in the Western Ghats over Kerala. We have taken the ground observation of micro rain radar from JJ season of 2017 to 2024. With the corresponding GPM DPR data. So first we have identified the all GPM overpasses over our MRR site, and we have performed a spatial collocation of 10 kilometer. And we have identified the ray classification category of nadir, extended or edge cases with the DPR scaling geometry technique, and after that we have made a temporal collocation with the MRR observation within a plus or minus 15-minute window, and finally we have extracted the DPR reflectivity and rain rate profiles and MRR reflectivity and rain rate profiles, and we have created an event-wise data sets of around 38 cases. So, and we have although we have got around more than 100 passes in the 10-kilometer collocation area, but the particular rain event that we shown here, like this, the warm rain like this structure, so we have identified only 38 cases of GPM passes over for such cases. So that was shown here, and in that 38 cases also, most of the time the DPR rain rate was 0, or for this low rain intensity GPM is not identified over the Western Ghats. So this is a scatter comparison of GPM, DPR near surface rain rate and MRR rain rate. So even though the scatters are temporarily matched, for the temporarily matched cases we have selected, so it shows a moderate correlation for the near surface rainfall. But for the higher rain rate, it shows a small bias, and why this bias is due, maybe due to the microstructural features. So we identified the vertical reflectivity profiles, near surface reflectivity of DPR and MRR, but it again shows a difference of plus or minus 5 to 10 dB, especially for the high reflectivity, that where the MRR shows low reflectivity for the light rain rate, and the DPR shows a high reflectivity for those cases. So for that one, we have further analyzed the full vertical profiles of DPR and MRR for those cases. This is the composite medium profiles of MRR and DPR. So it shows that in the near surface level, DPR shows a high value of reflectivity, and when aloft, it shows a very different. It shows a very weak gradients, but MRR is almost consistent from the top to bottom. So what we conclude that this DPR MRR temporal collocation is the bias between the DPR and MRR may be due to the vertical reflectivity, reflectivity and the beam filling bias. So this ground validation of MRR, ground validation of GPM distribution, GPM profiles with MRR like device instruments are very very essential for the Western Ghats precipitation studies. Thank you.
Thank you very much. So, questions?
Sumesh, there are two questions. Did you compare your MRR rain with your any ground-based measurement?
We have compared with the optical distrometer.
It is matching?
It's almost matching, around 4.7 correlation.
Okay, so it's matching.
Even in heavy rain situation also.
Okay, so that means your MRR is working. Did you try to do any frequency scaling, because MRR frequency is different and the KU band
right
frequency is different?
now we have not done any frequency scaling. So
if you do the frequency scaling, your both the line will match.
Okay.
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 Yeah.
Yeah. Any other questions? So you're comparing the Z profiles between the radar reflectivity profile between the KU band and the MRR.
K band.
So how about the calibration of MRR so that it's too large difference between the GPM and MRR. And do you have any idea of that?
Yeah, both are in different frequency range. That is, we have selected the KU band of the GM1, that is 35.6 megahertz,
Yeah.
6 gigahertz.
Yeah,
and
so
this K band is, MR is on K band, 24.5 gigahertz.
Yes, understand.
So
but
that frequency difference is there. But like Subrata said, we don't do any frequency scaling. So we have to do that.
Yeah, if you believe that both observation are correct, that means if you take differences between the two radars, that directly correspond to the drop size distribution or D0 or DM. So that maybe you can compare with that value with the MRR's spectral information. That gives also the drop size distribution information. So this is my suggestion.
Okay, sir. We'll do that.
In that MRR wavelength band,
yeah.
Liquid water absorption is one of the attenuation.
Yes.
Absorption. Did you correct for any?
Yeah, we have corrected that downdraft and updraft de-aliasing technique, and after that we have taken the profiles.
So liquid water correction you have
Yes.
done. Okay. And how do you know it is effective?
Huh?
Is it effective or?
Yeah. It is after correction. It is the reflectivity profiles are low values we are getting.
Mm-hmm. Because what I find is that it's consistently lower compared to your
Yes.
other one. So attenuation is one.
Yes.
Because, especially above 1 kilometer, it becomes a serious
Yes.
concept. Okay.
So combining both the things, attenuation will help you to derive the drop size distribution. That's like using the dual frequency ratio. That's how GPM derives the drop size distribution by using the KU and KA band. Okay, thank you so much.
Thank you.
So finally, the last speaker of the session and the last speaker for this iRAD 2026, Dr. Rashmi. And she will be talking about characterizing convective and stratiform precipitation microphysics using polarimetric radar and dynamometer observations over the southwest coast of peninsular India.
और अप एंड डाउन नहीं, इसमें हो जाएगा ठीक है. So good afternoon everyone. I would thank the organizers for meticulously organizing the conference, and moving on to my presentation, I will be presenting characterizing the convective and stratiform precipitation microphysics using polarimetric radar and distrometer observation over southwest coast of peninsular India. And here the mesoscale system, as everybody says, that it's a complex phenomenon, and it is always embedded with a number of microphysical processes. As we can see, it is convective nature of during the monsoon period also, the convective nature of monsoon rainfall that lead to the mesoscale cloud burst events. So the mesoscale convective system is not only present in the pre-monsoon and post-monsoon, but we can see the effect during the monsoon period. So that pose a great challenge for the researchers across. So for this study, we have taken the polarimetric C-band radar, weather radar, that provides the reflectivity, horizontal polarization, and differential reflectivity. In addition to that, we have used radiometer observation, micro-rain radar, distrometer, and lightning location network to classify the events that is installed at the National Center for Earth Science campus in the vicinity of the polar C-band radar within a 5-kilometer area. So with that, moving on to the data and methodology, we have classified the rain events based on the raindrop spectrum from the distrometer observations, where number concentration greater than 10 and rain rate greater than 0.5 millimeter per hour if it satisfies with rain rate greater than 1. We are also look for the standard deviation of less than 1.5 millimeter per hour. As you can see in the diagram, we are classified as stratiform stratiform, and else with a greater than 1.5 millimeter per hour, it's a convective rain. Else the system is mixed cloud rain for adopted from Lai et al. 2018. So in addition to that, again we have made an accumulated rain rate of 10 millimeter per event that coincide with the lightning occurrence as to select the convective events in a proper way. So hence we have identified 21 events in 2023. For this presentation I have taken 2 events, that is 3rd May 2023 and 2nd November 2023 as a pre-monsoon and post-monsoon event that lasted nearly 50 minutes with a cumulative rainfall of 29.87 mm. Another is 90 minutes, more than an hour, with a 31.7 mm. Moving on to the PPI diagrams, I draw your attention on the diagram on on 2nd May, 16 UTC, 17 and 19 UTC, where you can see the reflectivity profiles are nearly not there over the Arabian Sea. This is the coastal location and Arabian Sea and the surrounding the land region. So the cells are generated over the oceanic region of the Arabian Sea and in the mature and in the mature phase. So further along the convection line, we have plotted the reflectivity profiles, where you can see the reflectivity profiles along the convection lane where the storm height is up to 6 kilometer, and the micro rain radar also captures the reflectivity. So further radiometer analysis, microwave radiometer shows a deep layer of humidity profiles associated with the event, and it is also coincide with the lightning flash counts, and Cape supported by the convective energy in the Cape value, and it is this with the brightness temperature also shows a deep brightness temperature, deciphers that the selected event was a convective nature. Similar analysis we have done for the post-monsoon case also. So post-monsoon case, I can draw the attention where it is originated over the land region and in the mature phases and dissipated. So we have done the similar analysis along the convection line. We have to go along the convection line and again for the reflectivity profiles, you can see a much wider system, and reflectivity profiles of the micro rain radar shows a higher reflectivity extends beyond 6 kilometer. So again, the relative humidity, the lightning location network observations, the Cape, all shows the signature of a deep system. And further moving to the drop size distribution, that also shows a significant difference in the pre-monsoon from surface 1 kilometer 2 and 3 for the 2 cases. So I must and we have again done the physiologic algorithm to decipher the different type of hydrometeors along the convection line, where you can see the vertically integrated ice, high density graupel, and below 4 kilometer rain and drizzles in both cases. So I am not summarizing anything over here with the 2 cases, but I rather would like to draw the attention that the pre-monsoon and the post-monsoon convective events that we say per se we say, but it is need not be the overshooting clouds, or it need not be the clouds which needs to have a higher vertical extent. Both the events satisfy all the conditions of the convective event, from the ground observation, from the brightness temperature observations. All the conditions are satisfied this as a convective event, but the vertical profiles of the cloud that clearly says that maybe the congested clouds or a shallow cloud can give a much higher precipitation during the pre-monsoon as well as in the post-monsoon system. So I will, rather than summarizing, I will pose a question whether are the cumulus clouds or the congested clouds given this convective rain or not. So further analysis may help us to summarize the idea what sort of the cloud that hasn't really been precipitated in the pre-monsoon and post-monsoon phase over the coastal location. So with that, I will summarize. Thank you.
Thank you very much. So, questions?
Rashmi, thank you. So your results are actually not matching what we observe over our HACPL lab.
Yes.
Okay, so I don't know, means you are getting very small drops during this pre-monsoon.
Very high number concentration of smaller drops, and we took within 1 to 3 kilometer levels. Only the system having a different duration. Maybe it has a 50 minutes duration, it has a 90 minutes duration. So the microphysics process must be vigorous. That we can per se we can see from the micro rain radar observation in the ground level. Yes, I do agree.
Because the things is even not only Mahabaleshwar, but not with the literature, because convective rains are bigger drops and other things. So what is the large scale conditions, whether they were the same or some different like this?
Large scale condition, I need to check that, whether it is been supported by any system or depression system during those selected events. I need to check for that.
Okay, thank you.
Okay, thank you.
Any other questions? You have? No? Okay. Okay, thank you very much.
Thank you.
Yeah. So I'd like to conclude this session. Actually, we have various kinds of radar analysis using the dual pole and micro rain radar, and also spaceborne GPM TWIM and ASCII satellite, and targeting the mesoscale convective systems and also the lightning events. And it's really nice to hear the all presentation. I really enjoyed these presentations. Thank you very much for your joining.
Now the organizer has to announce.
Now I request Professor P. Chandrasekhar sir to deliver his lead talk. Professor P. Chandrasekhar sir, he would not be giving. I was being informed that he is giving. Okay, then it's valedictory session, definitely. Okay. Okay, take break. We will be assembling here after 5 minutes again. Okay.
Apni Kodok, we are at the end of the session. Good afternoon, everyone. Here we have reached at the end of this iRAD 2026. So I request everyone who is outside of the hall to please come inside. We are going to start the valedictory functions.
Good afternoon to one and all present here. On behalf of iRAD 2026, it is my honor to welcome our esteemed dignitaries, respected academicians, distinguished speakers, research scholars, and dear participants to this valedictory program of iRAD 2026. Your presence adds immense value to this academic gathering, and we are truly grateful for your time and association. To begin the valedictory program, may I kindly request our esteemed dignitaries to grace the dais. I request Professor B.N. Goswami and Professor B. Chandrasekhar to kindly take their seats on the stage. I also request Convener iRAD 2026, Professor Trubhajyoti Sohoria, to take the seat on the dais. I again request Professor Ramanujan to kindly take his seat on the dais. Thank you, sir. We now move towards the feedback segment of the program. I will. Okay. May I request Dr. Samiran Padgiri to continue with the program?
So here we have a very short time actually because people have to leave around 2:30 or like that. So we want to finish in half an hour or like. So we want some discussion or carry home feedback positives from one. So in this regard, I request Professor Chandrasekhar sir to come and give that feedback and remand carry away home from this conference.
Wait, you go sit in the empty chair. Go sit there. The people in the back, please come forward. Everybody come forward. You can't just sit in the back and look at. Come, sit down. I will, okay, thank you. When I say 1, 2, 3, we all have to get up and give a big hand of applause to the local conveners who have gone through a lot of effort. So, 1, 2, 3. Samiran, come here. Without their effort, nothing would have happened. And, he may have had so many sleepless nights, made late time calls. He didn't know what time was in the US. He would call me in the middle of the night. Or I will call him in the middle of the night. And he has worked with the committee so much. He has put in a lot of effort. Plus, I'm just keeping saying he. But he has a whole team behind him. Yes. So, if you want to say thanks to a few more people. This is your chance.
I will say at last, you carry on. I will say at last.
Okay, that's the first thing. That is profound thanks because, okay, then let me move to the next part. Next part is the student paper competition and young scientists. So we had a very interesting situation. First of all, I don't know, all of you have noticed, the quality of the papers have gone up since iRAD had started. In the first iRAD, all that you have to do was just show up. That was the criteria and talk something. But now, since then, more radars have come and people ask more hard questions. And that was the main purpose of this, is to intellectually stimulate the young scholars. And I had a slide, but I don't want to show it now. 2 years ago, the iRAD in Indore, and that iRAD, actually for the first time, they went through the review process, and it takes 2 years to do that. They have a book published on the iRAD proceedings. It was just announced by Springer Nature. And it was 2 years of like bare knuckle review, chasing the authors and review process. Of course, everything that was submitted didn't get accepted, but that enough articles raised above the bar. And then there is a volume that's coming out. It is just been announced. It will come out in March. So I want to actually congratulate the iRAD organization and the group of scientists to keep this up at least once in 2-3 years, we'll publish a volume. And because it's a refereed journal article, Springer Nature is well respected and so on. Then the third thing is for the young scientists and student paper competition, that also has gone up. And of course, there are, it's like, you know, the international cycling competition, marathon running. And so we had the whole committee yesterday, we had a struggle because we had people who placed very highly. At the same time, they have won awards before. And you can't completely eliminate them because that's called as punishing the success. That's a bad thing. But at the same time, you want to encourage more participants also. So we came up with a very clever decision, which is, that is, we will recognize the winners by name and so on. But if there is any subsequent further contributions, that will go to the people who have not won before, but still did win and compete with them on the first, second, and third prize. So this is finding a way of recognizing more people, at the same time not punishing for success. With that introduction, I'm going to invite the chair of the Technical Program Committee to announce the winners.
Yeah, like Professor Chandra mentioned, we are happy to see that we received 25 submissions in total, including YSA and SPC. And we shortlisted 6 for each of the category. And then it was a hard discussion. We thought we'll finalize this in 5 minutes, but it took more than half an hour to come to a conclusion. Yeah, first we'll go with the student paper competition. Yeah, so we'll start with the runner-up first. So Jagadish Jana. So we have 2 runner-ups. There was a tie. So Jagadish Jana, I request Professor Goswami to hand over the certificate. So we also have Ms. Arita BV as a runner-up, joint runner-up. Congratulations. Okay, so like Professor Chandra mentioned, so there are two winners. One we don't want to punish for success, and the one to recognize the new talent. So I would like to invite Vaibhav Tyagi. And Bijit Banerjee. Anyway. Congratulations to the winners.
That's all good. You know, they have to do a lot of work compared to others. They have to write a 10-page paper.
Yes. And the others are off by a little bit. It's not like there's too much contrast. The others are off just by a little bit. So. Okay, for now the time to announce.
That's another very important thing he said. People who didn't get awards are not like losers. It was all very close. But we have to choose some selection and then give something. So it was a tough choice. I'm glad you said that. Thank you.
Now to the Young Scientist Award. Yeah, so again, we'll start with the runner-up. Shruti Saini. Yeah, and we also have Ankan Basu. So we also have the winner of SPC, one not to punish the success and one to recognize the new blood, Yashwant Pulipati. and Roshan Kadbani. Yeah, so we are also introducing Best Poster Award this year. So we'll start with the third position, Raj Kishore Sharma. Sharik Khan, second place. Do you have Sharik Khan? Okay. And the first place goes to Samudra Borua. In absence, yeah. Yeah, so.
He's absent.
Okay. So with this, we conclude the prize ceremony. I would like to take this opportunity to thank all the committee members who deliberated and then took the hard decision. Professor Chandra, Professor Goswami, Professor Ushio, Dr. Uma, Dr. Manoj, Professor Bhatt in poster selections. Yeah, Professor Takahashi. And thank you so much.
So may I now request Professor Vianji sir to give some kind of feedback from this conference along with our conveners also.
Well, very short. We have to be adequate. Well, I don't really want to talk too much about it, but I think I just make a couple of observations, and then, because I have not been associated with this for a long time, but it was really pleasantly, pleasant to see so many youngsters coming in and presenting quite a lot of considerable quality work, and the spread of radar technology into the other organizations. It used to be only in IITM and IMD, but now it has gone to universities, IITs. IITs, they used to do only other kind of radars, but now they are going to weather radars. I think that is a great thing for our community. So that is one important thing that I find. And other thing that my observation is that I think this is a remarkable conference, and then I think we have three stalwarts of this in the world are here in this mall. To Professor Takasaki and Professor Ushio, they are all, the most, the JPM mission and the other missions he is talking about. So they are the top people in the world. And Professor Chandrasekhar, he is one of the topmost person in both ground-based radar and the space-based radar and everything else. So I think this is very fortunate, and I think very proud that this conference we had, at least we were able to have only 3 foreigners and only 3 outside people are the best in the world. So I think I'm very happy, and and that this conference is organized in this. My only request is that keeping in mind the importance of this northeast region and the northeast the topography and this interaction, we should have some recommendations coming from this to improve not only the observation network in this region, keeping in science in mind, and design some experiments which would help us understand this interaction between the small scale and the large scale in this region. So I think otherwise I'm extremely happy. 13 or 14 years ago, we started something in IITM, and I see there is a lot of progress has been made in terms of getting people trained in radar meteorology, and in terms of, but we cannot be complacent. There is a lot to do. So I think youngsters like Sachin and Subrata have to train people more to think more important science questions and the technological questions, how to improve the retrieval better and so on. So I think we have made great progress, but should not be complacent, need to do more work, I think. Thank you very much. So, and I, at this point of time, at least from the organizer side, I must say that some people have worked behind the scene and had made it success. Like Professor Saharia has chaired this committee, and there are few people here very much. I don't want to name everybody, but there are some people. Couple of them are sitting there, and they have worked tirelessly behind this scene to make this a circuit. And they have nothing to do with meteorology or radar to do it. And I must appreciate their contribution to this. Selfless service. And they have dedicatedly worked on it. Okay, thank you very much. And I hope that we will be able to welcome you again to Northeast. Thank you.
So I request Professor Thubajyoti Saharia to say a short word. Yes.
Thank you, Samiran. So I have very few words to speak. 4 months ago, our university assigned me and our few teachers, students, an assignment to hold this conference in our place. And if you are satisfied, you tell others, and if not, you tell us in what way we can improve better in future. And if somehow you are satisfied, then we believe that our mission is accomplished. Okay. And it's like when I be part of this organizing team, it's like a non-playing captain. Okay, so I am no longer associated with radar. I am from geography, so I could not take part much in your academic discussions, but anyway, we have discussed beyond your academic, outside this conference. We have got many new friends, many new discussions, and I believe that whatever new discussions assimilated in during this conference, it will develop some new concepts, new ideas to the radar meteorologists, or in long way, it will contribute the total vision of the country, that is the Viksit Bharat 2024/7. So if that somehow we can contribute to that goal, I believe that our goal is accomplished. So, but at the end, I must thank all my colleagues, and as I said earlier, that Samiran, Noirit, and then many more. I should not name one, but everyone have. Professor Modusri is here, and then Soyanika, then all the reception, Professor Sandana Sharma, Diganta is working on her transportation. So everything is done by very concerted effort, and we need not think of, actually all their parts are totally covered up, and we have got very good support from our administration, as well as from our sponsors. I thank each and everyone for making this a successful conference. Thank you very much.
So I request the steering committee and maybe some professors, yes, but if they have some positive figures, technical way, carry home messages from this conference, if you want to give some feedback, please help. Then any steering committee member who is sitting there, please, any carry forward message.
No, I think ask our foreign visitors this one, no? Them.
So thank you very much for giving me this opportunity to present at this conference. Actually, I think if I remember correctly, I first time attended the iRAD conference in Karagopo. I think that is my first time. So since then, maybe this is my third or fourth time to attend this conference. So I'm really grateful to be here with you. Thank you very much.
Okay. First of all, thank you, Samiran, for organizing nicely this much conference. Okay. So, yeah, so this is for the technical committee, another thing, because now as I came to know, like 25, 26 papers were there, and everybody has written a full-length paper. I think now it's time to revisit and think we should allow everyone to at least present their work. Because, 8 minutes is less, but they have given 10 pages. So I think it's now we can allow everyone to be part or participate in SPC and YSA, because in that way the things will goes on and increase. 5 and 6 limiting is just means it's. I think it's like a injustice to the person who has written 10 page, because the 10 page he can easily submit into some journal and maybe he can get a publication. Yeah, thank you.
Yeah, it's very pleasant experience here. I thoroughly enjoyed this. Is my eighth radar conference. Thanks to the conference organizers, I really appreciated the physical setup here, the excellent displays. The food was also very nice. We enjoyed all the foods and the dinners. The cultural night was also fantastic. Some suggestion? Yeah. So we need to actually do some efforts for bringing the enough participation from all the radar centers, because now we are having radars from IMD, IITM, and many more institutes are coming. So at least we have to ensure that enough participation from each of those institutes is ensured. So we have to give some recommendation for at least, otherwise it would be very difficult to attract the students or researchers who are not possessing any radars. So we have to ensure that there should be a mandatory participation from each institute. Otherwise it won't work, it won't sustain for a longer period, because over the last 10 years the number of participation is more or less between 18 to 100, the abstract submission. So we have to really think what extra we can do for increasing the number of participation. Overall experience is nice, and then I look forward for the next conference.
Thank you, sir. So any feedback from the participant? Please.
So I will also, this is my second radar conference. Earlier I attended the radar conference in Chennai. So I was also skeptical to come to far away to Guwahati, but still after coming here, I thoroughly enjoyed. And the scientific deliberations were very good. And the young students or researchers who are working in the field, they got a good opportunity to interact with the scientific team whoever has come over here. In that way, I must appreciate the organizers as well as the technical team, both, to have this conference in this manner. And I will also look forward further to have more radar conference in the near future. And that will, since India is going to have more radars in the country, we need to have a capacity building. So through this radar conference, we are in a way helping to the capacity building as well. So congratulations to all of them. Thank you.
Thank you, the organizers, for this excellent organization of the conference. In spite of financial shortage, I would say that first. Then the second point is that nowadays there are several radars coming up. But as far as the country is concerned, there is no consolidated place for a rigorous radar training or a capacity building. So why can't the iRAD propose a radar course? If you propose, we are ready to host, like universities, something like an integrated PhD or MTech PhD course, so that this trained manpower is available and it is ensured. So with the support of MOES, if we can do something, that's great.
Thank you for the suggestion. We'll try to implement that. Anyone?
I think this is on in the lines of what the previous speakers have said, but specifically considering the iRAD conference setup. So definitely, as IMD and everyone have been saying, that there will be more radars coming up and we need the manpower. The preschool was a good way to develop the capacity building in that aspect. But I would say that still, probably we can have more of that. One model that I find has worked well in international places is that they let the young people run the preschool themselves. So the senior people, they form a committee of early career researchers. They identify people whom they want to listen to in terms of the basics. They identify the courses they want to have. Not for long, just a couple of days before the conference. So I feel if we have a subcommittee with early career researchers, like a little senior ones, who can let the new people come in and, in place of a proper preschool just before the conference. So I believe that can be good. And of course, as Manojji said, we at ARIES can also host that if that is of interest and is being planned. Thank you.
Thank you, Guwahati University, for the nice 8th Radar Conference. It was a really nice experience with such a wide variety of presentations on the topics. So what I would like to say is, like, we should have one session on research to operations, as we are seeing that there are a lot of research activities that is going on, and those research activities should come into the operational to have an improved utilization of radar in the operational activities. If we can have one research to operation sessions in the iRAD conference, so then it will be helpful for both all the MOES institutes who are working on the operational activities. Thank you.
Yeah, thank you. I just want to make one suggestion. Maybe the technical committee may consider this. Like Guwahati University, when you organize one conference, we don't have much funding. We are not that rich, okay? So if there can be an account, maybe current account from this iRAD, if they register, and that can be floated on, and then the next conferences, whoever will conduct, that excess money will automatically, they will support that another one. I mean, like kind of change reaction. Yeah, that is my suggestion. Thank you. Yeah. I mean, no, it happens. It happens. I mean, you cannot spend all money unnecessarily. Yeah. First thing, iRAD has to register now. I mean, there are some society registration. Then once you have a PAN number, then you can apply for. No, I don't know. Yeah, maybe some of these guys we can discuss together. Yeah. I know. It's something like idea is yours, so you do. So yeah, that's a reason. So that can be done. I mean, this is feasible. I mean, then you have an account, then you can get funds.
You will do. We can introduce them.
Yeah, thank you. We can discuss it offline then. Yeah. Why?
It always happens. The moment you register something of that sort, it will at least become 1.5 times because you have to maintain the accounts, all of the details.
Yeah, we can discuss it. Yeah, thank you. Yeah. We'll discuss it offline with Subrata and Sachin.
So I would like to thank all the iRAD organizers for organizing such a wonderful conference. And I have one suggestion, like students like me, I'm a master's student. So registration fee was like too much for me, and there was no sponsorship at all from my university, and my guide, Dr. Sachin Deshpande, sponsored everything for me, and I'm very grateful to him. So one suggestion is if you can reduce the registration fee, and I know that there is like little less, all the things were there, so, but I would like to suggest this, if you can reduce it a bit, so more students can participate in the iRAD. And yeah, everything was wonderful. For me, it is like for my very first conference in this like iRAD. I have attended Intromet, but iRAD is my like very first conference. So yeah, that was the suggestion, and thank you all. The cultural function and everything was wonderful. Yeah.
Anyone else wanting to speak? Okay. In fact, I am very pleased to be here in this conference. Great to be coming back to Northeast after a gap of about 5 years. A few years back, I had trekked in Meghalaya region, again back here. An excellent arrangement. I was quite impressed by this display. We don't have this big screen in IISc, Yeah. So, excellent. Yeah, that's excellent. And thank you for the great hospitality and yesterday's cultural program, and nicely organized. Thank you so much. I see that there is a large group here who is using radar data and there's spreading. But when I speak to the young people who are working, one difficulty they face is getting data, access to data. In fact, like hydrological application or looking at some case studies, they want this data. And therefore, I think if we can make a recommendation to IMD from this team, saying that some special events, like either the cyclone or something which happens, on which many researchers may be interested, that can be put in a public domain where Indian researchers can access it. All you have to do is write to that particular data center saying that I want to access this, they give access and download. If that data cannot be shared publicly everywhere. This seems to be a common problem. Like they write to IMD, but sometimes they say we don't get any response. So what to do with that? So therefore, if you can have, means it need not be complete IMD data, but selected cases, you make it so that, next time you put a theme that you would like to focus on this, and many people look at that and they come back with their own version. It's like, touching an elephant. Different people touch different aspects. Often, they have different interests, but that will build what are the aspects of elephant. Okay? So if that can be made, I think it's going to increase the interest in this field, also number of participants, and also usefulness of radar data. Because right now, getting access to what they want is still a problem. Okay? So you can list that these are the cases where you can look at it. Many people can look at it. This is available. So if we can have some tie-up with IMD, because IMD is also part of this only. It is MOS event, saying that, okay, for this year, we are going to focus on this, and in fact, this data may be available at this location. IR conference website itself we announce. So people analyze, they come back with what they have done. Because that will be a great next level of activity. I can see that that will also increase the participation, especially from people who are doing PhD and other work. Okay, that's all I want to say. Thank you so much.
Thank you everyone for your feedback. So we don't have much time because we have to leave. So just before that, sir, I just thank everyone, right from that steering committee and technical committee, beginning with Professor Chandra sir, for giving us this opportunity of hosting this iRAD. 1 year back when I have met proposal, thereafter we are going meeting, and finally we have got. So it's a great honor to have you here. Thank you, sir, all the steering committee members. And I give to, so Professor Chandra sir has given me a special thank, but I am giving the thanks to my oldest committee members, sir, who has making this event into a reality, their hard work. So can I request them please rise, sir, all LOC member. All of them is not here. They have done great of job, but I please rise all of them. Right from every, if I started telling their name, it will go on 1 hour, you will miss the flight. So please have a round of applause from them, sir. Thank you. Because of this, we could able to make a success of iRAD. Hope we can meet you in future also. Thank you everyone.
So the next question people always ask is, where's the next iRAD? So it will be, we have about 3 proposals. So I will just list them in order. And one is from Cochin University, is that, or QSAT? Both are same?
Yeah, same.
Okay. So one proposal was from QSAT, and that has been a very consistent proposal. And then there is also another standing proposal from IIT Bhubaneswar, and then, but they all have to negotiate. And then there is another proposal from SPL, right? NCMRW. Oh, I didn't know there was one from NCMRW. Okay. And there is one from SPL. And so the bottom line is we have a committee, which is committee of past chairs who ran the IGORs, who have spent a lot of time. Now he's a new inductee into the committee. So that committee looks at this, and then, you know, and sometimes, many times, we let the people talk to each other, and it self-selects itself. We are never in a situation that we have to make the choice. My only hope is we get to decide very quickly, and hopefully before March or April, decide on this site. And then hopefully whoever didn't get it, who wants to participate next or something, it will somehow. What I'm saying is it's not like we just give this to somebody, or it's almost like a self-selecting process. And thank you.
Thank you. So may I request all the participants and dignitaries to proceed to that food court, that lunch is ready.